Sir, you may check once either you are able to share or not. Just you
Yes,
can
I'm
cross check
just,
once.
doing it.
Just I have stopped sharing. Just use cross check.
Is it visible?
Yes, sir. Yes, sir. It is coming, sir.
Okay.
Yes, sir. It is changing as well, sir.
So, can I start then?
Yes, sir. Yes, sir. I think we should start, sir. Still 60 participants are there, so slowly people may join. Okay, so very good afternoon, one and all present here. Thank you so much, sir, for accepting my request, our request to deliver one session on PMBLDC motor. With this, I would like to introduce our today's speaker for session second, Dr. Hitesh Kumar Kesri, who is the senior member now and received his BSc Engineering and MTech from National Institute of Technology, Jamshedpur, India, in 2003 and 2007, respectively, both in electrical engineering. And he had received his PhD degree in energy engineering from Department of Industrial Engineering, University of Padova, Italy, in March 2014. Since August 2015, he is with the Department of Electrical Engineering, Visvesvaraya National Institute of Technology, Nagpur, as an assistant professor. From 2006 to August 2015, he was with Department of Electrical and Electronics Engineering, BIT Misra, Ranchi, India, as an assistant professor. Dr. Kesri received silver medal for being first in MTech Electrical in 2007, Young Researcher Fellowship from Ministry of University of Italy in 2008, Erasmus Mundus Fellowship for 34 months from European Union in 2010, first prize as a student team leader of the University of Padova in class 3 of Formula Electric and Hybrid Vehicles in 2011. 2016 Best Paper Award of IEEE Transaction on Industrial Electronics and Visvesvaraya Young Faculty Research Fellowship for 5 years in 2017. His research interests include power electronics and electric drives for electric vehicle propulsion and charging infrastructure. Dr. Kesri has successfully executed project on wireless charging, temperature regulated fast charging strategy for VR, LA battery, development of PMBLDC motor drive, and design of 1 kilowatt synchronous reluctance motor for light electric vehicles. With the research grant and projects from DST and MIT Government of India. Dr. Kesri is associated with IEEE, IES, and PLS and contributed as chairs for technical track and special sessions in ICON 2013 to 2019. Dr. Kesri is contributing to Technical Committee on Transportation Electrification of Industrial Electronics Society, IEEE, as chair of TCT. So thank you so much, sir, for being with us. Thank you so much. Please, you may start your session now. Thank you, sir.
Thank you, Kundan sir, for inviting me for ATAL program for the faculty development. I'm grateful to you that you invited me. And to the audience, I just wanted to let you know that it was a great pride for me that I was in past. I also worked with Kundan during our PhD program. So we are also Guru Bhai.
Yes, sir.
There he was working on resonant converters for the charging infrastructure. Of course, we were in a different project, but we were having good interaction for technical. We were having good technical exchange also during the different projects. So let me first share my screen. And before just going ahead, I just want to request all audience that please ask the questions. Okay, it is not like that you keep your questions, what you are coming into your mind during my discussion or presentation.
Excuse me, sir.
Yes.
Shall we ask the questions in between or in the end?
Yes, surely, surely. You please feel free to ask in between. You can stop me anywhere, wherever you are facing problem.
Okay,
Like
sir.
if you think that you are not able to understand, you stop me there and ask me to explain you. So I will be more than happy for that. Okay, so please ask the questions. So whatever the experience I have, it is true that in 2 hours we cannot complete everything. Rather not 1 hour 45 minutes something. But if some of the questions I'm able to clear, then it will be very good. Okay, so please ask, even though like you are not able to ask right now, but you can definitely ask me the questions after also, or you can mail me also. Just a moment. So please let me share my screen. Okay. So this PMBNC motor drive actually is my major, and my PhD was in this area, and since 2008 I'm working in this particular area, and we had developed this particular course for the students of University of Padova, a master student, together with Professor Bhuja, who was my supervisor. And of course, like here, whatever I am discussing, it is just a portion of that course. So let me start my discussion. So when we talk about the BLDC motor, there are some, definitely you want to know that what are the different books or papers what you can refer. So I suggest you that please go through for the more information. There is IEEE proceedings, okay, of proceedings volume number 9 of 2007. Okay, actually this proceeding have a total 9 number of papers which relates with electric vehicles and different areas of electric vehicle. At that time it was relevant, still it is relevant, and in future also it will be relevant. Okay, so it is all for all to go, those who are interested in the area of electric vehicle, it is good to go with read all the 9 papers of these proceedings. Then there is one they have explained about the different types of motor used for the drives. They have been explained there very nicely, and it is explained that which motor is good for which. You will then you find that for the light electric vehicle application, these PMBNC motors are very good. For mid-duty vehicle like car and etc., this PMSM drive is very good. And then if you go for the heavy vehicles like trucks and others, so there you will find that induction motors gives outstanding performance. Okay, so it is not like that you cannot use this motor for another purpose. You can use all the motors in different segments, but when we talk about the best performance, then that is the criteria. Okay. Then there's one book by T.J. Miller. In this book, you will find that they talk about permanent magnet brushless motor. I also started with this one, and they also talk about the reluctance motor drive. So the 2 reluctance motor we know. One is switch reluctance motor. We are well aware of about that one, and then synchronous reluctance motor, which is going to be future. Okay, so it is very good for us as soon as we adopt with this synchronous reluctance motor. Okay, because they have good performance as compared to the induction motor, but yes, they are non-permanent magnet type, so they have not that much capability as that of the permanent magnet motors. Okay, but they meet the requirement of high speed cruising and all. Then there is another paper. It is overview of permanent magnet brushless DC motor drive. motor drives for electric and hybrid electric vehicle. Okay, it is in 2008. This is also a good one. So all about everything here it is discussed about. Then one paper I have included here, which is my own paper, which carries out the analytical discussion on the torque and speed characteristic, where we try to represent the motor torque with torque behavior with the characteristic of the motor, and that also got when you will read, you will find. Okay, so there we try to explain you what exactly is the PMBNC motor and how its characteristic changes with the speed. Okay, so these are suggested readings. Then I will not read the definition completely. You can definitely read here. So as per the definition, we can define a vehicle as an electric vehicle if final tractive power, okay, the final tractive power means that the power which is required for the motion of the vehicle is being delivered through an electric motor. Okay, that doesn't matter from where you are getting the energy. You can receive the energy from onboard IC engine, onboard batteries, fuel cell, photovoltaic panel, whatever it is. But yes, the final tractive mean should be your electric motor. Then we say that it is an electric vehicle. Of course, yes, we can definitely tighten the norm, okay, to meet our another requirement that we are moving towards electric vehicle only with the two objectives. One that we want to improve the performance of the vehicle, and second one that we want to reduce the emission. So both are these objectives. So if someone asks why we are moving towards electric vehicle, so we want improved performance, or means better performance, and then at the same time we also want to have the reduced emission. So this is the objective. Okay, so basically you can see here a vehicle is termed as an electric vehicle if it uses electric motors to drive the wheels directly or through differential gears. Okay, if you have a central motor, then you need differential gear. And if you have motors which are embedded with the wheels, then you don't need differential gear. Okay, so they will be receiving energy either which is fully contributed by the onboard DC source such as battery, fuel cell, PVs. Okay, or you can receive a portion of the energy from the onboard IC engine also. Of course, in this case, you have, because onboard DC source available, so size of the IC engine will be lower. Then we say a vehicle is a pure electric vehicle if you receive whole of the energy from the onboard DC source. But the moment you receive even a portion of the energy from the onboard IC engine, then it will be termed as a hybrid electric vehicle. Okay, and another thing is that you know that which motor we are using, as per that we classify the drive. So we say, like, suppose the induction motor, so it is an induction motor drive. A synchronous motor, so it will be a synchronous motor drive. So likewise, there are it is like a practice to term the motor drive. So here in electric vehicles, the drive we are going to discuss about permanent magnet brushless DC motor drive for electromechanical energy conversion. Then, okay, before going ahead, it is good to explain you something about like, because we just have used the name PMBLDC. Okay, so what exactly it is? Is it a DC motor or a synchronous? In an AC motor, it is good to know. Okay, just to explain you what I'm using, let me explain. Suppose that you all know about a synchronous motor. So here basically we are trying to learn the name of this, like why this PMBNC or another name is there. So let us consider here you see. So at present I'm trying to make the representation of synchronous motor. Okay, so let us consider this is the electromagnet which is there, which and being used as a rotor. So we know that in synchronous motor we give the excitation, DC excitation externally. So, and with the DC excitation, what happens here? It produces an stationary magnetic field flux is there. Okay, we can write it as phi rotor. Now, if you start rotating this rotor, so what will happen? Rotating this rotor, this flux will get linked with the winding. Okay, here. So you have the three-phase windings, phase A, phase B, and phase C. A, B, and C windings are there. So depending upon the nature of the winding, if it is distributed, okay, so this flux linkage, stationary flux linkage with this distributed winding is going to result into a sinusoidal back EMF. Okay, it is going to result into a sinusoidal back EMF. This is, let's say, that electrical angle. And if the winding is concentrated in nature, just like that the case of the DC motor, you'll find that the nature of this winding is trapezoidal in nature. It will be something like this. Now, because this motor is a synchronous motor, so we know that to obtain the maximum torque per ampere, we need to inject a current, which is, these are back EMF basically, okay, back EMF. We need to inject a current which is synchronized with the back EMF. So in case of distributed winding where the back EMF is sinusoidal in nature, to obtain the maximum torque per ampere, you have to inject a current, sinusoidal current here, okay, phase current. And similarly, in this case, you need to inject a current which is synchronized with the flat top portion of the back EMF of the motor. Okay, this is your current I. So here everything lies now. So whether it is a synchronous motor or permanent magnet synchronous motor, this definition is going to remain. So when this type of representation is there, where the back EMF is sinusoidal in nature because of the distributed type of winding, it is called synchronous motor of AC type. Okay, and this one is called trapezoidal back EMF, is called synchronous motor of DC type. Why? Because when you are going to calculate the torque, this is only one phase. Likewise, we will have three phases. So you will find here that only two phases are conducting. So the power is what here? This is E and this one is I. Similarly, minus E and minus I will be there for another phase. So it is going to be 2EI, and this magnitude of this flat portion is represented by K omega m. Omega m is the mechanical speed, just like the case of the DC motor. So the total torque in this case, total power is twice E omega m, and sorry, is K omega m. So I K omega is m multiplied by I. This is going to be your electrical power. And if you consider there is no loss, then P by omega m, loss in the power transmission to the shaft. So it is going to be 2KI. Okay. So this torque is appearing similar to that what we have seen in case of DC motor. So mainly synchronous motor of DC type. Now what we do, and definitely this is given through the brushes, this excitation. Okay. Now here in the same case, if we just remove this winding, suppose that we remove this winding here, DC excitation externally here, and what we do that we just remove it. Okay, we just remove this one, and in place of this winding, like that electromagnet of what we have used, now if we use a permanent magnet, no, and south. Okay, here also let me try north. So but we first thing what happened, that we do not have any brushes to connect here, so it becomes brushless synchronous motor in this case. So the next nomenclature will be what? Brushless synchronous motor of AC type and DC motor. Now because you are using a permanent magnet here, so it becomes permanent magnet brushless synchronous motor of AC type, permanent magnet brushless synchronous motor of DC type. So some people also say that permanent magnet brushless motor synchronous motor of trapezoidal back EMF type, okay, or non-sinusoidal back EMF type, like this also they will say. Okay, so you see that this is the nomenclature which is appearing here. So some people say it is as a PMSM motor in general, okay, for both this and this. But PMSM with trapezoidal back EMF, PMSM sinusoidal back EMF. Some people will say it as PMBL AC motor, permanent magnet brushless AC motor, and permanent magnet brushless DC motor. And then this term becomes so popular, then people started saying it as BLDC, BLDC, BLDC. But please remember that it is a synchronous motor in which the rotor is a permanent magnet, okay? And when we say DC, it means that the winding is concentrated type and, okay, concentrated type. And to obtain the maximum torque per ampere, here we need to inject the square wave current. Because of that, you got a torque just like a DC motor. So it is like this. So you say that permanent magnet brushless synchronous motor of DC type, or simply PMBLDC motor. PMBNC Motor. So I hope it is clear to you, because before we go ahead, and of course in some cases, like people give the logic that here that the voltage source inverter, what it is used, that acts like a electronic commutator in place of that mechanical commutator which was there in DC motor. So to some extent they are also correct, okay, but we have to, like, from where the concept is coming, we have to know that, okay. So this is, so it is not like that this is a DC motor, it is a synchronous motor. In DC motor also, you just give the excitation, it will start rotation, but in this case you just give the supply, it is not going to rotate. The supply should be synchronized with the rotor position like this, then only you will be able to rotate your motor. I hope I'm clear here. Okay, so if you have any doubt, you can ask right now to me. Okay, so let's go ahead. Now, about the electric vehicle, in brief, it is very important to let you know, otherwise topic will not complete. So if you see an electric vehicle, now we are talking about the case of pure electric vehicle. Okay, so onboard system can be classified as a supply system, traction system, control and monitoring system. This is all on board. Okay, and then there's the offboard system also, that is your charging infrastructure. Here I am representing, sorry, AC to DC. Here I am representing with the grid, but it is not necessary that here it will be grid. It could be a photovoltaic panel also, or fuel cells also. Okay, or it can be mix of grid with photovoltaic panel, fuel cell, or it can be mix of grid, battery storage and all those things. So it depends. So this is representing your charger as well as a charging station. Okay, so offboard system is what? Charging infrastructure. Okay, supply system, traction system and control system, and then charging infrastructure. Okay, so in this traction system, you will have a traction motor together with a voltage source inverter. Please remember that if the traction motor is AC in nature, then you need a voltage source inverter. But if it is a DC motor, then you don't need voltage source inverter. Rather, you need a DC to DC converter. Okay. Then control track supply system. In supply system, you can have the combination of energy sources and power sources. Energy sources are what? Your battery, fuel cell, okay, fuel cell and photovoltaic panels. These are the energy sources. And power sources are what? Ultra capacitors and flywheel. Characteristic is that these energy sources have the capability of delivering a nominal current for a longer duration of time, and this decides the range of your vehicle. Okay, and the power sources, they have definitely the capability of delivering very large current, but they can deliver you for a very, very short duration of time. That is your like transient operations such as acceleration. Okay, and when the energy recovery will be there during regeneration, they can accept that bulk amount of energy. Okay, that is the situation here. So, but here in supply system, there's a possibility that because your intention is that you want to run your vehicle for a long duration of time, as well as you also want to have better performance during the transients. Okay, so at that time you need to use this power system, means combination of energy source as well as power sources. Okay, so the moment you will be using the multiple sources, then in that case there's a need definitely of using different types of power electronic converters. Okay, mostly like we use a boost converter here. So supply system consists of a combination of the energy sources and power sources. First thing. Second thing is that we need multiple energy. So these power electronic converters in case, two cases. One, that you are going to prefer the combination of the multiple sources. One. Second, second is that and major is that onboard this DC link voltage is higher as compared to the supply side voltage. Okay, that this energy source voltage higher because that you have to keep the terminal voltage of the motor high to reduce the copper losses here, and but these energy sources are capable with the lower terminal voltage. So to bridge this gap, you need to use power electronic converters, because let's say that this is 24 volt and this bus is 48 volt. So what you can do, you have to boost it to match this higher DC voltage. So you'll have to use this arrangement. Please remember, with the batteries, we generally go for the series connection and we go for the power electronics converter arrangement for only those sources where the output characteristic of the source varies, such as photovoltaic panel and fuel cell. Okay, because there you need to maintain a particular operating point. And control and monitoring system, it is obvious, we know that we set some reference, so it forces the system to operate to meet your references, and at the same time it takes care of the state of the system, how the temperature is varying of the different parts. One, then what is the terminal voltage, what is the current, everything it try to monitor, which is used to ensure the performance of the vehicle. So these are some examples where like this is an electric assisted cycle, which is using hydrogen fuel cell. Then it is an electric bike, and then it's a small city electric car. Okay, these are some examples. Then now let us move to our agenda, the traction motors. Okay, so traction motors are basically
load the generator na
Is there any question? Okay. So, so now next we are moving to
Me, sir.
Yes. Yes, please tell me. Kundan? Is there any question? I think there's no question. Kundan, am I audible? There is something in chat box. Let me see if something is written. No, nothing is written at present. Fine. I think I go ahead.
Yeah, audible, sir. Continue, sir.
Okay, please. Thank you. Thank you. Okay, so let's move ahead. That then the question arises that what are the characteristics of a traction motor? Like, can we say a normal motor as a can be considered normal motor also as a traction motor? So definitely no. There are some requirements. Requirements are what? Like okay, all these points are taken from the paper of C.C. Chan. Okay, C.C. Chan. So like there's a high torque and power density, high starting torque for low speed and high power for high speed cruising, wide speed range with a constant power, operating range 3 to 4 times, high efficiency over wide speed and torque range including low torque operation, intermittent overload capability, typically twice the rate of the twice the rated torque. Okay, and reliability is must, and the cost is also important. So all are different points. So let me explain you first point. When we say that the torque density and the power density is high, it means what? We are talking about the compactness. Suppose that there's a motor A and motor B. So if we say that motor A is having higher torque and power density, then from the size point of physical size point of view, it will be quite compact, rather B will be larger. Okay? B will be larger. This is like from the size point of view, physical size point of view. Second point. So please see, we all know about this famous characteristic curve of an electric drive. Here it is the speed of the motor, and here let's say the torque. So we know that we can represent it as like this. So reason here to here it is called constant torque zone operation. Okay, constant torque zone of operation, and this one is constant power zone of operation. Constant power zone, okay, of operation. So important. So here the torque remains constant. This is average torque. Please remember, huh? And this particular point is called your rated speed. So I am writing rated. When I am writing omega, it means it is in rated per second. Now another thing is that for your motor to run, okay, to operate, there is some minimum torque requirement. So like this one, minimum torque requirement for a vehicle to run. So this is the minimum torque which is required. So if your drive is not able to give the torque more than this line, then you will not be able to run your vehicle. Okay. So this is decide that what can be the maximum speed of your vehicle, motor, and so. Okay. Now we say the maximum torque during the starting. So what exactly is the meaning? Suppose that there's one candidate motor is like this and another candidate motor is like this. Okay, so there's a difference between the two. Okay. What is the difference? So in this case, let's say that in one case, I'm making same point, huh? Where this is for power. So this is the situation. And let's say that another case is there. So in which this is the situation. For an example. Okay, so in this case, you see that the A is there and this is B is there. So here it is possible to see that you can observe that the torque being offered by the motor during the low speed is higher. Okay, so we are going to prefer this. Why? Because we all know about the speed torque characteristic of attractive load. This is omega and this is, sorry, let me change the axis here. This is omega m and this is torque. So because as we have read in the book, it is good to draw in the same way like this one. So this is the starting torque when the speed is 0, the load torque is higher, and when you keep on increasing, that this reduces, and then finally you have this situation. Like we have studied this, the behavior of the. So once it starts running, we don't need that much of torque. Okay, so at the beginning, it is always good that you have the higher starting torque to overcome this issue. Okay, so that's why a motor with high starting torque is good for us. If you have a high starting torque, then you will have better acceleration to reach to your maximum speed. Okay, so this is the case. Second is that we say that it must have high power for high speed cruising. What is the meaning of this one? So here, like you see that one is this situation and another is, let's say, this situation. For example, like this one I'm making here. So what you are going to prefer? Two characteristics different I am preferring. So here in this motor, the maximum that you can go up to this speed only. But in this case, because the power is higher, so this curve is definitely going to be upper than this one. So you can see that in this case, it is possible that you can go for even higher speed. this A, B name I have given, omega m B, and this is omega m A. Okay. So we are going to prefer definitely this one. Okay. And the third point was here that wide speed range with a constant power operating is 3 to 4. Means what? That you see that omega mb or omega m is there, and this is omega rated. So what omega m A or B we are saying about, that must be 3 to 4 times higher than the rated speed. Okay. Means this width should be 3 to 4 times larger than this one for a motor to qualify as a traction. Suppose that your motor is 1,000 rated speed 1000 RPM. So you should be able to run in the constant power zone or cruising, during cruising at 3000 RPM to 4000 RPM. This is the meaning. Okay. Efficiency, I'm not, then important intermittent overload torque capability, typically twice the rated torque. Means when you are, let's say, accelerating, so at that time you need to draw or you need to deliver higher torque. So that for that short duration of time, your torque must be this 2 times what the nominal torque is there. You can consider this is as a nominal torque. So during acceleration, your torque should be 2 times of this one, 2T. So of course, 2 times of this one means 2 times current also you are going to draw. Okay. So these are different some characteristics of a traction motor. Okay. So now let me go ahead. Okay. And so the different candidates are what? That induction motor, switch reluctance motor, what is SRM motor, permanent magnet brushless motor, and another motor is now we are also studying in our lab about this. We fabricated 1 kilowatt synchronous reluctance motor. Okay. This is SynRel motor. So mostly people have used it for constant speed application like pump and others, but now all are trying to adopt it for variable speed application like Tesla has also considered. But in that you see Tesla and Toyota, you'll find that they have used permanent magnet assistance because these motors are basically reluctance motor. They do not have any back EMF. So the problem is that starting torque is less here, so you need to improve the starting torque. And second thing is that it is if the back EMF is not there, okay, then it is difficult to identify the rotor position also. So this use of permanent magnet in synchronous reluctance motor with the name permanent magnet assisted synchronous reluctance motor, need that assistance also. So let's go ahead. Now, so if you look into your traction system here, as I explained you, here you have a traction motor, which is now we are using a PMBNC motor and a voltage source inverter, which responsibility is what? To inject a current which is synchronized with the flat top portion of the back EMF. Okay. Now, here, so here you please see that this is a case of an in-wheel motor. Sorry, okay, in-wheel motor here. It is the case of an in-wheel motor in which you can see that the motor is fixed with the wheel itself. Sometimes it is called hub motor also. Okay. And then this PMBNC motor, they use the information of Hall sensor, information from the Hall sensor to know where the rotor is. Okay. And then from there, they try to select the switches. Okay. And as per the reference, these selected switches are modulated. And then finally, the gate pulses are being gate pulses for the switches to modulate are generated, and those gate pulses are given to the corresponding switches to operate. Okay, this is the insight of this one. So in this case, you can have a look here. Go inside, the winding is there, and then here you have a Hall sensor here mounted. These Hall sensors are 120-degree apart from each of the phases, which are 120-degree apart also. They are leading by 30 degree around. So this is the Hall sensor. Here you see. all sensor. And then here this is the voltage source inverter. Okay, and it is an interface circuitry for to operate this voltage source inverter. And the batteries are there. So let us go ahead. So different classification. I will not put much emphasis on this one. So basically permanent magnet brushless motors are radial flux, field machine, axial field and linear field. Radial field means this is, you see that this is the shaft. If the flux is linked radially like this one, like if you look from this side, okay, like this side, just look from this side. So you will see the circle. So this is that circle. Okay, so if you're linking radially, then it is radial flux machine. If the flux is axial to the shaft, like this, you see, this is axial flux machine or axial field machine. And the linear means, you see that for stator and rotor, it is linear. So not so. So it is linear field machine. Okay. Then depending upon the back EMF, I explained you, it can be a PMBNC motor and BLAC motor. Then your motor can be surface mounted. This permanent magnet is mounted on the surface, or it can be mounted on the surface but buried inside. These two cases are for PMBNC motor. Okay. Similarly, like there's another case for IPM motors, interior permanent magnet motors, in which your magnets are buried, something like this one. IPM motors. These are good for PMBNC motor, vacuum sinusoidal. Okay. In this, you will find the reluctance torque is also available. Then depending on how the magnet is placed, if arc magnet is 180 degree, here you see well, it is 180 degree, so it is called 180 degree arc magnet. And if the arc magnet length is 120 degree, it is called 120 degree arc magnet. Difference between the two is that in 180 degree arc magnet, your stator winding will be star connected. Okay, star connected. And in case of 120 degree arc magnet, stator winding will be delta connected. Okay, this is the situation. Done. Now, here in this case, at a time, only two phases are going to operate to obtain the maximum torque per ampere. But here, at a time, all the three phases will be conducting. You can see that the phase current, these are phase currents. Okay, these are phase currents. They are, you can see here in this figure, first figure A, that they are 120 degree spanned. 120 degree spanned. Phase A, and similarly, there's another one is phase B. Okay, 120 degree apart, and then third one is phase C. Okay, in this case, the current here IA, IB, and IC, like these one, IA, IB, and this is IC. These are of 180 degree spanned. Okay, but if you look like this current, IA line, IB line, and IC line, you'll find that they are again IAB, IBC, and ICA still 120 degree span. So from control point of view, there's no difference. Same algorithm will be suitable, will be working for this motor as well as this motor. Okay. Next. Then you can represent your PMBNC motor through with the representation three-phase RLE load, R, L, and E, phase A, phase B, and phase C. This is the voltage source inverter, and this is the supply voltage. So you have the three back EMFs you can see here, which are displaced from each other by 120 degrees. So you start from here. After 120 degree here, each section is 30-30 degree. Okay, and then third one is starting from here. So each back EMFs are displaced from each other by 120 degree. Okay, 120 degree. And here you see that the current, phase A current, is synchronized with the flat top portion of the back EMF. Here similarly, the current phase A is synchronized with the negative flat portion of the back EMF. Similarly here, okay, and similarly in these cases. You see that? So corresponding phase currents are, each of the phase currents are synchronized with the corresponding back EMF. And this is why we are doing so, because we want to obtain maximum torque per ampere. You remember that earlier I had written equation E, and this is I, and this one is minus E, and this is E. So the EC, and the third phase is here. Just we are considering this line. Okay, E I. So minus I E, and here E is I is 0. So what is the total power? EI plus EI to EI. So from here we were getting EI, and minus I minus E. Okay. So, but this is the requirement. So next my intention is to discuss with you about like this. Okay. Now, it is important for us to know that how this motor is actually rotating. If you don't know this, then you will not be able to operate the motor. So to understand this, first we try to understand that what is the principal operation, like some equivalent arrangement we have considered. So that 180-degree arc magnet is there. So it is replaced by what? North and south pole. Please remember that this 180-degree arc magnet has a flux like distribution, field distribution like this one. Okay, this is okay, electrical angle, and this is there. This is pi, and this is 0, and this is 2 pi. Okay. So this one is replaced by a bar magnet, and all these windings, you see that AA, this AA is there, coming here, and it is going there. This winding, concentrated type. Okay. This is replaced by what? Flux like this one, because of this one. So we replaced it by a bar, by equivalent electromagnets like this one to get like this phase. Similarly, phase B is there, BB is there. You see, it is like this. So because of this, flux will be in this direction. So we have put one magnet here and another one here, like here. You see, yes, see. Okay. Similarly, phase C is there. Phase C is this one. So it is coming like this, going in, and like this one. So in this direction it is. So this is phase C. Okay. So how we can obtain? You have to put two electromagnets like this, north and south, and only it is possible to rearrange like this. Okay. So equivalent representation is this. Now let's go ahead. Now, important. Once again, I am drawing that ahead. Body diodes also I am drawing. Okay. This is the, okay. And here phase A, phase B, and phase C to the motor A, B, and C is there. Please remember these switches are 1, 3, 5, 2, 4, and 6. When you give this current, like upper switches are coming, so they are like here IA is positive, here IB, this is A, B, and C. So when the current is entering here IA, IB, or IC, then they are positive. And when they are leaving from here, when they are leaving from here, IA, IB, and IC from the lower switch, it will be negative current. Okay. So here you see that here phi A is because that here you have given a positive phase current. The switch A is on, switch 1 is on. Okay. So you are getting 0 and plus I. So in this case, flux is in this direction. Okay. Similarly, in this case, you see that when the switch, lower switch of the phase A is conducting, so in this case, the current will be in this direction 0 and minus I. So what is happening here? You see that the flux just reverses its path. So in this case, it was like this. So similarly, we can do for all the cases. So here you see that I is positive, and similarly here B is what? Here you are giving positive current 0 plus I. That's why you are getting like this. And here you are giving positive current, so 0 and plus I. Why? C is positive. Why? Because you have turned on switch phi here plus I. Then you are getting the current like this. If you just reverse it, okay, it will change the direction. If you just reverse here, phase B is this, na? 0 minus I. So what the flux was in this direction, okay, B na, this one B, it will change its direction. This direction. Similarly here, it is very important for us to know. So positive means here switch 1 is on. IA positive means IA positive represents phi A positive. IA negative represents phi A negative. Similarly, IB positive represents phi B positive, and IB negative represents phi B negative. IA is positive. Why? Because you have turned on the switch 1. IA is negative. Why? Because you have turned on the switch 4. Okay, similarly for other pages. Okay, so here you see this is one case just to understand. So what we have done, that we have given phase A current as a positive. So here what it is, phi A plus, and this is phi B minus. This I'm not going to make all, just I'm making this representation. So IA positive means switch 1 is on, and IB negative means switch 1, 3, 5. Okay, and 2, 4, 6. Switch 1 and 6 are on. Switch 1 and 6 are given high pulses, so that they are on. So this is the situation. So what flux they are converting? 1 is positive, so this is phi A, and B is, you see, negative. So it is going to produce phi B minus. So the resultant of this one will be what? Stator flux phi S. So your rotor, this rotor will try to, phi R will try to catch it and get synchronized, like here in the second direction, your diagram you're seeing. Now, if you don't make any further excitation, what will happen? That it is not going to move further. Please remember. So to make it to move further, you will have to change the excitation. What the change in excitation will be? Now you see that IA plus and IC minus is there. Okay, so IA plus is what? Is still phi A in this line, and IC minus is phi C minus. Where is phi C minus? This one. So this phi B minus is now off. So you see that now this and this is there. So your stator flux is. So what will happen? This rotor is now going to move in this direction further. So what you are observing, that it moved here further. Okay. Similarly, you can see, so you are trying to keep that rotated. You see, now again it is IB plus and IC. IB plus is what? Phi B, and IC minus is phi C minus. Where is phi B? This is phi B. Let me erase it. So you see, in this case, so here the situation is here. You see that phi B is there and phi C minus is. So stator flux is this direction. So it will again try to move. So this continues. So this is compulsion for you, that you have to keep on moving after each 60 degree of interval, because the flat top portion is 120 degree span. Okay, then only it will be possible for you to keep your motor rotating. Okay, so you can see that it is rotating, and if you want to have reverse rotation, then you will have to write your code accordingly, sequence, so you can move your motor in forward and reverse direction. Okay, so we understood this, like how it can be rotated and what is the necessity to keep on changing the excitation. Okay, otherwise you will not be able to rotate it. Now we need to run our motor, because we have to control it. So to run the motor, we know that this is a synchronous motor. Okay, important, it is a synchronous motor. So that's why we need to know where our rotor is, and according to the rotor position, we are going to inject the current into the motor so that our motor will rotate. Okay, so how to know the rotor position? So to know the rotor position, this Hall sensor plays an important role. Okay, now here you see that this is phase A, phase B, and phase C. So 30 degree apart it is, ahead it is 1. This is 30 degree, this is 30 degree displacement. Now how it works, I just let you know. Let me once again go with the diagram. So one, two, and this is 3. Okay, let me change it. Let us consider that this was South Pole, this was North Pole. Now this is North Pole and this is South Pole, means it is rotating basically. Okay, and this is the center position. So this was our south pole and this is north pole, central position. Okay. So now what it is done, let us place a Hall sensor here. So please remember, let's say that we are putting a Hall A. Same thing, Hall A and Hall A. So this Hall is what? It is, the motor is rotating. So at this position, you see that this flux is going to get linked here. So it is the minimum one. So corresponding to this, you will see that EMF is going to get induced into the Hall. So here it will be minimum and it is going to be maximum, and then again it is going to be minimum. That flux linkage with the Hall sensor. Okay, and again after 120, so this is what 0, this is pi by 2, this is pi, and then again after 2 pi, it is going to start this position. But you please remember that if you have this one, then you will face problem in identifying the distinct positions. So for that, what we do, that we try to use edge, like you pass this one, okay, edge detection, make a biasing, let's say 0 to 5 volt, you are making biasing, and then you are giving this Hall signal here input, then you will find that wherever it is becoming positive, you will be getting a high signal. So after passing the edge, you will get a high signal here. Okay. So when south pole approaches, it becomes high, and when north pole approaches, it becomes low. You remember that I had drawn that B line like this. B for the motor, this is B. Because of the 180-degree arc magnet, this is pi, and this one is 2 pi, like this. So this is the Hall sensor signal what we use for our identification. So because 3 phases are there, so another phase will come what? Hall B will be there, so that will be after 120, this 120 degree here. So Hall B will be starting high here, and then it will go low again. Similarly, Hall C will start somewhere here, and then again it will go up. So if you check, you will find that there are 6 distinct positions here: Hall A, Hall B, and Hall C. You see? So these Hall sensors gives us the information of 6 distinct positions. This is 1, 2, 3, 4, 5, and 6. Half here and half here. So you see that this is high, this is low, and this is high. Similarly, high, low, low, high, high, low, low, high, low, and likewise. Okay. So this is giving us information. Now, please relate this Hall state. So these are called Hall states. So 101, 100, 110, 010, like these are called Hall states. Okay. So please relate it with, go ahead. So this is Hall A. So please observe where the Hall A is becoming high, at the same time, the positive flat portion of the phase vacuum A is starting. And where the Hall A is getting low, that is what? The position where the negative flat portion of the back EMF of phase A is starting. Okay. Negative, it is starting here. So what is happening? Hall sensor is starting from here, and it is continuing up till the negative flat portion of the corresponding phase. Like this, it is starting. So we are getting information. Okay. Now wherever the Hall A starts, it means that we are the start of the phase back here. Similarly, you see that Hall B is there, it is starting here. So where you see that here, phase back here for Hall B, phase back here is starting off for the phase B. It is starting here. Okay, and you see that it's a negative flat portion is starting here. So what we have done, you see that this Hall is like this. So Hall B is starting here, and it is continuing up till the where the negative flat portion. So clearly we are able to identify that there is a relation between the back EMF and the Hall states. Okay, so this information is known to us. Now next is important here, that you see that where the Hall A is starting here. So back here current to be injected is what? Like this one. So where see EA is positive and here IA is also positive. So how IA is positive? If you turn on the switch 1, then only IA is going to be positive. Because for IA to be positive, you have to inject a current which is into the this one. This is A, this is B, and this is. So if you turn on this switch IA, okay, switch 1, 3, and 5, 2, 4, and 6. So when you turn on this switch, you'll find that the current is positive. Otherwise, it will not be possible. Now, you need what? Here, negative flat portion of the current with the negative flat portion of the back EMF, this one. So when it is possible, when the lower switch will be turned on. So lower switch is what? When the time will come for that this one here for the lower switch, this switch to be turned on. Then only it is possible. So we are getting relationship also here. Like when 101 hall 5 and hall 4 is there, 101 is 5 and 101 is 4. So when hall 4, state 5 and 4 are there, switch 1 to be kept on. Okay. When hall 0, 0, 1, 0 means it is what? Hall state 0, 1, 0 means it is 2, or hall state 3 is there. When the hall state 2 and 3 are there, then switch 4 should be turned on. So we are getting information here from the Hall state. So here what we done, we got to know about the relation between back EMF and Hall state, and we are also getting the information about the relation between the Hall state and the current which is required to be injected. Let's go ahead. Okay. Now what is to be done here? You please see here that we got to know that we have to inject the current like this. We have to inject the current like this. Okay, this is 120 degree spanned. So this is 120 degree current we have to inject. Okay, so there's a one in operational topology of the three-phase inverter we have studied, that is 120 degree mode of operation of the inverter. So in what is the need to inject the current? See, we need to inject the current because we want to generate electrical power. Okay, electrical torque basically we generate. Back EMF is available here. Okay, this back EMF is there, but how you are going to generate power? Because it is electromechanical energy converter. Unless you inject the current, so here if you inject the current I, then what is the power for this phase? EA multiplied by IA. EA multiplied by IA. This is the power. And what is that? The magnitude is E and this is I. So this is the power. Similarly, second phase is there. This is C, phase B is there. Na? So here which current is to be injected? Here you see. What is the source? Just a moment. Okay, so question is what is the source to inject the current? It is onboard battery we are considering. So here, is there any question? Okay, no. Okay, the source is what is the need to inject. So you got to know that if you, unless you inject the current, you will not get the power here. So then you will not be able to develop the electrical torque. That is needed. And just now I explained you about the flux that your motor to be, you need to rotate your motor. So you need to inject that current, otherwise it will not be possible. And from where we are getting the supply? Just go back. You see this is the inverter supply system, here onboard battery is there. This one. Plus, minus. We are getting supply from here. Okay, am I clear to you? Plus minus from the battery, plus and minus. Side engine, is it clear to you? Okay, fine. Let me go ahead. So here what we do, that 120-degree mode of operation of the inverter is considered here, and we are considering here, you see that you can consider zero position here itself. TQ TQ for detail. Okay, okay, sorry. You're too short. Huh? Thank you for detailed explanation. Thank you, thank you. Just a moment. Huh? Someone waiting. Okay, so this is the zero starting position. You see that here. So T1 to be turned on. So here you see 30 degrees, and this is 60 degrees. Please remember, huh? 30 this is, but the large one is 60. So you see that here you turn on your switch 1. So this is IA will be there. Okay, similarly to switch, this is I4. Where is there? This is there. And for the rest of the duration, this is. So if you realize these two, when the turn comes, then you will be able to realize this current. Okay. So in any case, for 120-degree mode of operation, switches are turned on in the interval of 60 degree. You see, 60 degree. And once they are on, they continue to conduct for 120-degree duration. So this is 120-degree duration they are conducting. This is 1, 2, 3, and this is 4. And this is 1. Okay. So you see that in one Hall state, let's say this is 5. This is 5, 4, this is 6, this is 2, 3, and 1. Half of this one is here. So if you want, you can extend this one. This one. 0, 0, 1. Half is this side. Okay. So 5, 4, 6, 3, 2, 1. This is the sequence. And what are the switches conducting here? You see that here switches conducting are 6 and 1. Then 1 and 2. Please check 1, 2. Then 2 and 3. Then 3 and 4. Then 4 and 5. Then 5 and 6 and half. Here it is. 5 and 6. So you got to know that when the Hall state is 5, switch 6 and 1 are to be operated. When Hall state is 4, switch 1 and 2 are to be operated. 6 is the Hall state 6 is there, the switches 2 and 3 are to be operated. So this you are getting the information, but you have to segregate take out the gate signal. 6, 1 is there, means separately you select 1, and then whatever you want to do, modulate, not modulate, that is to be decided by you. Okay, that you have to do. So next is that, so this is called, this stage what at present we are seeing, that identification of the Hall state and then switch selection. So switch selection is yet not completed. You are knowing the pair of the switches, then you have to make the OR operation of this one. So to explain this one, I think I can explain. You can definitely write down a MATLAB code, but here we can explain like this. This is Hall A, this is Hall B, this is Hall B, this is Hall C. Okay, so these are Hall A, Hall B, and this is Hall C. And then you see that here, and basically this is what AND operation, 1, 0, 1, high, low, high. When all these combinations are there, then only you will select the switch 6 and 1. So the AND gates 1, 2, 3, 4, 5, and this is 6. So this is 1, 0, 1. This is 1. All B is 0, so use NOT gate, and also is 1. So this is 1, 0, 1. Similarly, we can make for others. I will just make 1, 1, 0, 0. So this is what? Oh, this is 1. This is 0, and this one is 0. 1, 0, 0. So likewise, you can form for all. Okay, so then it is what? 1, 1, 0, and then 0, 1, 0. It is 1, 1, 0, 0, 1, 0, and then it is 0, 1, 1, and 0, 0, 1. 0, 1, 1, and 0, 0, 1. So you can make the combinations here and make it. So here, what are the switches selected? Switch 6 and 1 is selected. Here, which is selected? Means 2 in 1 and 2. Then here, 2 and 3. And then here, 3 and 4. Then here, 4 and 5. And here, 5 and 6. These are to be selected. But you have to select individual switches. So here, again, you have to take OR operation when both are common. So which is common? 1. Similarly, here you have to operate So here switch 1 will be selected, here switch 2 will be selected, whichever is common. 3, switch 4, switch 5, switch 6. Okay. Switch 6. So you see that here you will be getting all the high gate pulses here. So whenever the term of the corresponding switches will come, you will be able to generate these gate pulses. Okay. So this is generated here. These switches gate pulses are generated. So this is called switch selection. Okay. Rotor position identification from Hall sensor, and then switch selection. Then next step will come what? Switch modulation. About 111. Where is 111? It is not there. 111 is not there. 11 means what? All the upper switches are on. All the upper switches are on. When 000 is there, means all the lower switches are on. This is the meaning. So, but here we need these 6 different distinct states. Am I clear to you? Sai? Okay, thank you. Okay, so this information is known to us. Now at present, let me explain you further. Okay, so this is done, like we are able to identify the gate pulses and all. Okay, here now important is that what is our intention? Now we are moving towards the control. We are moving towards the control. Okay, so we know that when you are going to do like this at a time, how many phases are going to conduct? Only 2 phases are going to conduct. Phase A, phase B, and phase C. Let's say switch 1 and 2. This is the state. Sorry. Let's say we talk about here, this one. So switch 6 and 1 are operating. Only one, this one. One state we are talking about at present, this one. Switch 6 and 1 is conducting. So let me go ahead and show you something. So when such a situation is there, so what will happen? Switch 1 and switch 6 is on. Switch 1 means what? Upper switch of the phase A is on, and switch 6 means what? The lower switch of phase C is on. So what you have done, you have given the high pulses to this high pulses, and this phase is not conducting. Phase A, this is B and C. This C is not conducting at present. This is not conduction. Okay, so here you have given high pulse, this is switch 1, and this is, and here you have given the high signal, gate signal, not high pulse, high gate signal. So these two are going to conduct only. So due to this, what is the voltage of this point? This one, so this is VDC with respect to negative terminal of the battery. What is the voltage of this point? You see, this is with respect to negative terminal of the battery, this phase B point, this is 0, and this one is DC. So what is the voltage appearing here? This is VDC. So this will be equally distributed. So it is VDC by 2, and here it will be VDC by 2. And if you measure in this direction, so what will the voltage for this be? Minus VDC by 2. So let's say this is neutral point, and so VAN is your VDC by 2, and VBN is equal to minus VDC by 2. This is what is appearing. And so what you are going to do here, you see that you are having a back EMF. To inject the current, what you are going to do, you are going to apply a voltage here. For phase A, I am considering only. Okay, you're going to apply voltage here like this. Okay, this is what? This is VAN, and the magnitude is what? Plus VDC by 2, and when this term will come, it will become what? Minus VDC by 2, and this is your EA. And so when such a situation is there, because voltage is supplied, voltage is also fixed. Okay, what will happen? The current will rise with its dynamics, and then it will settle down and go down. Okay, and then it will rise with its dynamics. Okay, and of course there will be some problem of commutation. I'm not making it, but please remember, when you are fixing this voltage, means you cannot use it for variable speed drive application. Rather, it will be a fixed application. But if you want to use it for variable speed drive application, you should be able to change this applied voltage. Okay, this applied voltage. Okay, this applied voltage. So accordingly, you will be able to change the current with the injection. Okay, you will be able to change the current, magnitude of the current. So you will be able to change the torque also, depending on applied. So to do that, it is preferred to modulate either upper switch or lower switch. Okay, let us consider that we are modulating only upper switch. And what is the condition for the modulation? We want current control. So we sense the DC link current here. Okay, DC link current reference you set. Okay, how it is? You are basically setting torque reference. So torque is 1 by 2Ki. So divided by 2K is what? You get the current reference. Okay, remember that in the steady state, like here, what the current is entering, the same current is going out. Okay, here what the current is entering, the same current is going out. Just a moment. Huh?
I'm not getting any voice.
So here you see that the same, if you control this DC link current, then indirectly, because the same current is flowing through that phase A and phase B, so you will be controlling phase A current or phase B current indirectly. So, and how to do? So this IDC reference is set. So IDC is there, then you have a PI controller, then 0 to 1 duty ratio limiter, and then you modulate it. Okay, compare it with the carrier signal 0 to 1, and then finally you will be getting a PWM. So this is delta PWM for current control. Like some people don't want to make the current control, they will be making voltage control. So okay, no problem. You sense this phase voltage and then set the phase voltage as a reference and feedback this voltage. So output will be what? Delta PWM with respect to voltage. Okay, so this is done. Delta PWM I. Let's go back. So now you see that, like, you have to decide now. You have this delta PWM with current control. Okay, you decide which switches you are intended to turn on. Let's say that we intend to operate upper switches. So upper switches are to be again ANDed with these signals. Upper switches 1, 3, and 5. And rest will remain as it is. Okay, so here what you are giving now, like this one, and here what you are getting, high. So wherever both are high, you will get high, otherwise you will get like this one. Okay, similarly here you will get. So whenever the turn of these switches will come, they will get modulated. This is what? S1, this is S2 unmodulated, the S1 modulated, S2 like this, S3 modulated, this is S4, this is S4 modulated, and this is S1, S2, S3, S4, this is S5, no? S5, and this is S6. So you see that you will be able to modulate it now. So you will be able to change this voltage. This is modulated. So what will the voltage of this point? Delta VDC. So what will the voltage here? Delta VDC by 2, this delta VDC. So you see that you are able to change this applied voltage. So now you are making something like this. Okay. So you will be able to regulate the current. You see that you are able to regulate the current. You will be able to regulate the current of the DC motor as per your requirement. So what you will be seeing here now, because you now modulation, so you will be seeing like this. These are the gate pulses. Okay, so you will be seeing that the current is getting regulated. You see that I'm not doing anything to this part. This is DC link current control. You are not regulating this zero reference current. But when you go for phase current control, you even regulate that part. So your current will be regulated. Sorry, I did mistake now. like this. Okay, but when you'll be going to DC link current code, you will find such type of problem. Okay, something like this. Such type of problem will come. So this type of waveform you would have seen that if you worked with the oscilloscope. Okay, so this type of response you would have seen. Okay, in any case, so now we have generated our gate pulses. Okay, we have generated our gate pulses. So what we have done? Switch selection, sorry, Hall state identification, switch selection, and switch modulation. So let us go ahead, and I just want to show you, not this one. This is the case what we were discussing about, DC link current control. So here you see that with the Hall state, we were trying to find out the Hall state, and we were giving the switch selection and modulation, and then 6 gate pulses were generated, which were given to the voltage source inverter. And this is the DC link current, what we were sensing it. Okay. So this part we had discussed about. Now there is another one also. We'll come to this PI control. Okay, but there is phase current control also. In phase current control, what we do, that we sense the current directly, phase current directly. Rather, in the previous case, what we were doing, we were sensing the DC link current. And in the steady state, we're knowing that that same current is flowing through the phases. Okay, phases. So we were identifying that. And then indirectly we're trying to control those current. But here in DC link current, in phase current control, directly we control the phases. But yes, there's some issues here. In this case, it is like only having the information of discrete Hall information is not sufficient. Here we need to know what is the continuous rotor position. Information of the continuous rotor position is must to have. So here you get the Hall sensor, and from the Hall sensor you estimate the rotor position, and then you know the theta is, so you generate the current reference. And how the current references will be generated? It will be something like this. Okay, it will be something like this for phase A, phase B, and phase C, all 120 degrees twist. They will be generated, and then you need to use 3 PI controllers. In this case, limiter will be minus 0.5 to plus 0.5. Okay, advantages, like in this case, the whole leg of the inverter, this is one. Whole leg of the inverter is acting as a one entity, and they are synchronously operated depending upon the value of delta A, delta B, and delta C. Wherever in the previous case, you were selecting the switches and then modulating them. So same situation is not here. This is the difference. And the advantages or disadvantages, like this phase current control arrangement is very good when you for the low speed applications. Okay, when the motor is running at low speed, and then you want to make it appropriate control. But for high speed operation, like both DC link current control and phase current control gives you same performance. There's no meaning. But like in some cases where you have, let's say, trapezoidal back EMF, but you are interested in injecting sinusoidal current or the current of your requirement, then in this case, it is very important for you that you must know what is the rotor position. Otherwise, you will not be able to. So this type of arrangement is possible only with phase current control. Okay, so how you can do it? Hall state, speed estimation you have to do, then rotor position estimation, and then you can generate your references, either square wave or sinusoid, like what I had explained you. Okay, then problem is that if you want to know that rotor position, or speed estimation. Rotor position is also, you know, speed estimation is very, very important. So for that, you can consider any of the Hall state. Okay, and then from there you start counting until the falling edge comes. So from here to here you count. Okay, and then you, so what is this? This total duration is T by 2. So multiply by 2, that is going to be the total time period. So T is known to you. So 2 pi by T is the speed of that electrical speed here. Okay, so you are able to know it. Then, and second approach is that you measure only like rising edges. Like here you see that rising edge of Hall A is coming. So you start counting and you count up till the falling edge of, let's say that Hall C is coming here. Okay, rising and falling edge you detect of different Hall states, Hall signals here, here. So you will have the information after each Hall state, 60 degree. So this duration is known to you. So multiply it by 6. So total duration you will be knowing. Estimating future one. Okay, so then again you can estimate the speed. So once the speed is known to you, then you can predict that angular position. This is a way. Okay, like this one, you see that you need to know the rotor position. Size order, if you want to inject, you do like this. Okay, now next issue is that we have seen that if we want to have the current control, then we need to use a controller. So let's learn something about current control. Okay, current controller. So for this, you remember that I explained you here that this motor can be represented by what? RLE load. So we are just considering one of the phase R, because we phase current we need to control BAN. Okay, so IA we need to control. So BAN information is must. So here you see that here we have considered phase only for phase A. So R, L, and E. So this is BGO means voltage of this terminal with respect to negative terminal of the battery. Vn is the isolated point. You do not have access of this one. So Vn like this, and this is Ez. Let's go ahead. So here we are considering one of the phases. Let's say phase A. Phase A we are considering. So here phase A is what? You can see that we can write down the equation. BAN is what? Here to here. BAN minus IRA L minus LDI by dt plus EA. And what is BAN? BAN is nothing but BAO minus VNO, voltage of the neutral point with respect to negative terminal of the voltage, and BAO is what? Voltage what is applied by the inverter, that is delta VDC or 1 minus delta VDC, depending upon your operating upper switch or lower switch. Okay, so let us consider. So this equation is known to you. Take the Laplace transform of this one. So if you take the Laplace transform of this one in what? BANS, then IS will be out, and then R plus SL, okay, plus ES. Rearrange it, bring it to this side. So BAN minus ES divided by 1, this one. You see, this will come. So here actually 1 by R plus SLA is there. Then you take out R outside. So that's why you see that the 1 by R is coming. So it will become 1 by. Okay. So LA by R is written as electrical time constant tau E. Here. Tau E. Okay, EN minus ES. Similarly, motor torque is, we know that Tm is equal to 2Ki, E is equal to K omega M, and mechanical dynamics, Tm minus TL is G omega dt plus B omega M. Take the Laplace transform, so omega M is equal to 1 by B, 1 plus S tau M is times tau S. Okay, this is the situation. And tau M is what? J by B. Okay, so now next is that you need to connect all. So here you please see that we started with VANS. What it is there? Minus EA, EAS. Okay. Then we have this block 1 by R plus 1 plus S tau E. Okay. So what we are getting? IA. Then IA is what? IA multiplied by 2K. That is motor torque. Then motor torque minus load torque. TLS. Okay. Multiplied by this transfer function. So 1 by B, 1 plus S tau M. Yeah. Then it is your omega ms. Okay. And this omega ms, where it is multiplied by K, is K omega M at the back here. Okay. So this is the diagram, block diagram representation. Now, let me go ahead. So see what we want? We want current control. So where is the current? This one is that current. So this current is made as an output. So this is 1 by R, 1 plus S tau is like this, and rest all these terms go into the feedback like 2K. You see that everything is in feedback. So we make like this one. Like this we are making. Now you can solve it. What is our intention now? Because we want, and this PI controller is what? Transfer function Kp tau is plus 1 by tau E. This is the transfer function of a PI controller. And these are parameters of the motor R, then B, J, tau M, all. So here it is IAS. Yes.
군단 오자 군단 기억 없이 벌싱하니 비게 에밍 합신기 하보할 나는 안돼 말 락너리 어두 도리 행시 지는 아심.
Okay, fine. So this is IAS over I references. So what you need to now know? You have to know what is the overall transfer function. This IAS and this is I references. Now, this is you have to find. So one way is that put TL is equal to 0 or is reduce it, and then finally you will have one block, and then further solve it, then you will have another block. Take the product of these two. Okay, G1, G2. Okay, this one, let's say that it is G1 and this is G2, and then, so overall transfer function will be what? G1, G2 divided by 1 plus G1. But this approach will become quite complex, so we prefer to have a simpler approach. And what is that? So in simpler approach, one concept is there, like you see that you have a back EMF like this, back EMF like this, and the current which is required to be injected is what? It is like this. Okay, so you see that current loop is much faster than the back EMF. See this variation much faster than this one. So in that situation, we can consider it neglected. So if you do like this, you are left with only this one. So you have PI and this section. Take the product of this one, and then you have the transfer function like this. The reduction of this one. You solve that, and you will find like this one. Okay, transfer function. Now, next is that we want to have to bring it into the standard form. Okay, so what is that standard form? In the standard form, if you represent it, it is S square plus twice zeta omega ns plus omega square n. Okay, and then here it will be omega square n, and some term will come. Like this it will come. So you have to bring it into standard form. So you take out this, okay. So it will be what? Tau E, tau I, here tau E, tau I, and here it will be tau E, tau I. Okay. So now you have s square plus this one is twice zeta omega ns, and this one is omega square n. Okay. Compare these two. So you will find that twice zeta omega n is equal to, this is cancelled, 1 by tau E, 1 plus Kp by R. Rearrange it. So from here you will get Kp equal to twice zeta omega n tau E minus 1 multiplied by R. This one. Similarly, for the second comparison of this, okay, you will get tau I is equal to this value. So important here is that if you observe that the values, what are the values known? R is known to you, electrical time constant L by R is known to you, then R is known to you, electrical time, these are known to you. But what are unknown? Damping ratio zeta and natural frequency, these two are unknown. Okay, so this damping ratio generally we keep around 0.7 to 0.8. Okay, and then damping ratio we can keep from 700 hertz to 1 kilohertz. This bandwidth, F bandwidth. Okay, 700 hertz to 1 kilohertz. So what will be the natural frequency? 2 pi F bandwidth. And what is this bandwidth? See, bandwidth is known, so you can know that what is the reciprocal of this one. So time is known to you. Okay, so all the operations right from the acquisition, from the sensor, current acquisition or whatever it is there, acquisition, then processing in the microcontroller, and then finally writing the value to the pin where the driver circuit is connected, and the action of the driver circuitry to the switch. All those time must be completed within this time. Then only your control will be realized. If that is getting exceeded, or that time is, if say that time is more than this time, then your control will not realize. Realized. Okay, this is the problem. Okay, so here we learned about how to find out Kp and tau I. So once tau I is known to you, so you can find out integral gain as Kp by tau I. So this is the approach generally we do. So like here today we learned about what is like an electric vehicle system. Then we learned about what is a PMBNC motor. Then we try to understand the nature of the back EMF. Then we try to understand that to obtain the maximum torque ampere, the current should be injected in synchronous with the flat top portion. Then we try to learn that how we can control this motor and what is the necessity of giving the excitation to the motor in sequence, proper sequence. Otherwise, motor is not going to rotate. Then we learned that, okay, now everything is known to us. So how we can run our motor? So to run the motor, we need to know the current should be injected in synchronism with the flat top portion of the back EMF. So to do that, first we have to know Hall state. From the Hall state, you have to identify the switches, select the switches. For the case of DC link current control, I'm telling you, the switches are selected, then you need to modulate that as per your control, whether it is a current control or voltage control. So here I explained you about the DC link current control. So you generate the PWM reference, duty reference for the current control, and then you compare it with your carrier signal to get the PWM generated output. Okay, and that is given with that duty, with that PWM, you modulate your switches which are selected, and then what happens that with that you are able to run your motor. And then I explained you about the how to calculate the PI controller in your controller. So these are all about from my side. So now I'm open for the questions. Let me see that if I missed some of the questions which were there during our discussion. The question was, Torque 2KIY multiply with Y. No problem. Let's go ahead. Here you see. This is phase A, phase B, and phase C. Phase A back up is EIA. Phase B is EB, current is IB. Phase C is EC, and current is IC. What is the total electrical power generated? EA, IA plus EB, IB plus EC, IC. Let us consider this state. Okay, this state we consider. So in this state, Hall state, what is the situation? EA is E. What is IA? It is I. What is EB? It is minus E. EB is minus E and IB is minus I. Okay, what is EC? EC is changing from positive to negative, this positive flat portion to negative flat, and IC is 0. So what is the total electrical power? This is EI plus EI, that is twice EI. Okay, and what is the magnitude of this one? Winding is concentrated type, just like DC motor, is given by K omega M. So we know that. So what is the electrical power? This is twice K omega M I. IA is what? I is the DC link current, same, this ID. Or phase current, because in steady state all are same. This ID is capital I. And we know that torque is what? Electrical power by mechanical speed. Assuming that there is no loss in the shaft of the motor. Okay, so P is what? 2K omega M I divided by omega M. So it got cut. So tau is equal to 2K I. Psi, am I clear? That's why we multiplied by 2. Any other question? Let me check if I missed something else. What is BLDC? So I have explained, I think, to you. Okay. BLDC is that, like, people are now using PM, saying that permanent magnet brushless DC motor is the full name, but in short they say that brushless DC motor. Okay, you can say brushless direct current motor. Yes. But it is a synchronous motor, not a DC motor. Then inject this, I explained what is the need. Okay, so is there any question? Kundan, are you there? So you can ask me the questions, audience. And if there is no question, then we can close it. Okay, fine. So I think there is no question right now.
Dear participants, you may ask questions if you like. If you have any query, you may ask, please.
Kundan, I think there is no question.
Yes, sir. Till now, I'm not able to find any questions there. Maybe
Okay.
if you
Then can I leave now?
just wait for 1-2 minutes, sir. Not then you may leave. Just wait. If okay, you may leave. Like, just wait for a second, sir. Let me do my own work. Just a second, sir. No any questions from audience side? Just a second, sir. Okay, so there is no question, sir. Once again, thank you so much, sir, for your kind support and very informative session. So thank you so much, sir, for accepting our request and delivering a very informative session. So if there is no questions, you may leave, sir. That's your.
Okay, Kundan, thank you. Thanks.
Thank you so much, sir. Okay, sir. I will contact you later on, sir.
Sure.
Thank you so much, sir. Thank you.
Bye.
Dear participants, third session will start at 3:45 and the speaker is Dr. Ranjan Kumar Behra from IT Patna, and he will be delivering a lecture on electric propulsion system design with electrical motors. So please, you may take a break for a while and kindly join, or maybe you may stay here. Please join at 3:45 for your third session of the day. Topic is electrical propulsion system design with electrical motors. Thank you so much. Hasni, are you there? Am I audible to everyone? Is it audible?
Yes, sir.
Okay, thank you so much. Okay, so very good evening, sir. Now we have with us Dr. Ranjan Kumar Behra, sir. Very good evening, sir. Welcome to the third session of the day, sir. So people are joining. Still, we have 51 participants, including us. So let me introduce our today's speaker for third session. Dr. Ranjan Kumar Behra received the Bachelor Engineering degree in Electrical Engineering from the Regional Engineering College, now NIT, Rourkela, India, and the MTech and PhD degrees from Indian Institute of Technology, Kanpur, India, in 1998, 2003, and 2009, respectively. He worked at Hindustan Aeronautics Limited, Sunapeda, as training engineer. Since May 2009, he is a faculty member in the Department of Electrical Engineering at IIT Patna, where he became head of the department in January 2016 to 31st March 2019. During July 2008, February 2009, he was a visiting scholar in the Energy Systems Research Center, Tennessee Technological University, USA, and also a visiting research collaborator at ECE Department, University of Pretoria, South Africa, during July 2016. He got several national and international awards such as Young Scientist Award in Engineering Sciences from DST, Government of India. 2001, selected as the featured engineer of the globe in 2015, USA, and Bhaskara Advanced Solar Energy Award, Indo-US Science and Technology Forum in 2014 for doing solar research in Energy System Research Center, Tennessee Technological University, USA. He published more than 134 research articles in different national and international journals and conference proceedings. His current research interests include power electronic, high power motor drives, smart grid, and IoT applications. He is a co-authored a book that entitled Power Electronics, Drives, and Advanced Applications, CRC Press, in April 2017-2020. So thank you so much, sir. Please, I'm handing over the session to you. Please, let's start, sir.
Thank you,
Your voice is
it
low.
okay? It's not audible?
No, it is little better, but still very low, sir.
Low voice. So let me start from my maybe. You can hear.
Sir, is it audible?
Yes, sir. Yes, sir. No, proper.
So thank you, Dr. Kundan. Although you discussed about me, but I am also a student. So I learn from this and I try to improve myself. So any where you are stuck up, so you can just stop me and I will discuss that. Okay. So today we will discuss on the especially on the drives. Okay. Sir, is it visible to everyone?
Yes, sir. Yes, sir. It is visible, sir.
Okay. So today we will discuss about the electrical propulsion design with electrical motors. Although I worked in many electrical motor control, different kind of propulsion drives, and such as induction motor, permanent magnet synchronous motor, BLDC, and hub motors also we started developing now. And also some special motors and the SRM other things we done. But here we will only discuss the two very important motor, that is the open end winding induction motor, which is used in the 4-wheel dual motor drive and 3-phase motor drive. So already this is already discussed by. So research activity here, we do the solar, wind, power electronics, wireless power transfer, and smart grid, electric vehicle design, renewable energy. So there are different research activities and products which we develop in this laboratory, and we have a book this. So today the main objective is what are the challenges and introduction. And if you see there are a lot of challenges. Now people want to use the mid-drive motors. Their mid-drive motors are synchronous motors are there, brushless DC motors are there, and now induction motors are there. So if you see,
Is the speaker voice is audible to everyone? Because I am not able to listen.
Oh,
Yeah, audible, sir.
Audience, can you respond, please?
Audible, sir.
Audible, sir.
Audible, sir.
Fine, sir. I think sound issue is there. So
sir, you are not able to hear me?
others are able to listen.
Yeah, sir. It is clear.
Okay. So actually,
Okay, sir. You carry on. Maybe
started
there is
my
some issue
mobile,
in my side.
from mobile, the audio and from this. So if you are not audible, then I can stop my videos also. If bandwidth is.
So you're audible clearly, sir.
Okay. So we will discuss a few control techniques in this electric vehicles. And if electric vehicle propulsion, we got a project from National Mission on Power Electronics that initial we got this one to design an high efficient the induction motor for the propulsion application, where we designed that motor around 110 volt, 80 hertz motor. So for the wide speed range, and these are the requirement that time. And we also developed that motor with the help of an industry from Bangalore. And this motor also patented and patent also accepted in 2020. So the EV propulsion motor, they should have a high power density. If you see today, power density in all kind of motors, two motors are highly power dense motor, that is today permanent magnet synchronous motors are treated as a highly power density motor. But there are also the problems with the magnet because rare earth magnet, we depend on China, which is very costly. So now next motor comes as an induction motor, so it is very easily manufacturable. And in India, everywhere you will find this induction motor very easily. And people also speak about the hub motors or in-wheel motors. So this time we have developed an in-wheel motor which is sponsored by NEMI Electric Mobility. And it is not till today developed, but the design is freezed. Just last week we freezed the design. Maybe within few days that motor will be available in the Indian market, where it is the first time that motor will develop, which is a very high density, even better than the synchronous motor, permanent magnet synchronous motor. And second one, high torque at low speed for starting and climbing. These two are very important. And that is why this is series motor we use in the Indian Railway as a traction motor. But nowadays we use also induction motor where the AC drives are used nowadays. So this high torque at low speed, because at low speed you require high torque because there is a stiction. Stiction means the internal friction between the rail and the wheel. Wherever the tire or wheel is there, that is during starting time there is a stiction. So large amount of torque you require to overcome that frictional force. Okay. And then climbing also another important thing when you have a electrical propulsion system. And high power while cruising, that is also another important because you use this the batteries as the power source. So that is why this is also another important thing. And wide speed range, including constant torque and constant power is there. So why this wide speed is required? Because if you see in Indian roads, the wide speed range may not be required in other countries like America, other countries, they may not require. Whereas in India, you require because there are a lot of humps. And if you the road condition also many places are not good. So in those periods, you need to extend your speed range because you need to control both way the 4-quadrant operation. High efficiency over wide speed range. Nowadays, electrical vehicles are available, but in the all speed range, you cannot get higher efficiency range. If you can design a controller such that the 20% speed also, it will give maximum efficiency, 50%, 50%, 70%, 100%. At all the speed range, nobody could able to design till today the efficiency optimization technique by all this speed. Efficiency is not always high level. There are a lot of changes. Okay, that sometimes you will see that at a base speed, you may not get high efficiency. So at a higher speed than base speed or lower than that. That is why if somebody can design a control system which will give you like a VYF control, means always the frequency remain constant in all linear range of the change in the voltage with respect to frequency. So similarly, change in the with respect to the speed to the your power, if it can remain constant, the efficiency, that will be good invention. And today, everywhere people are trying to get this wide speed range with high efficiency. And there are a lot of talk on this. If you see, there are one technique, the maximum torque per ampere, maximum torque per voltage is a new concept which is coming for the electric vehicle, because in the electric vehicle there is an inertia. When that inertia torque is released that energy, the DC link capacitor voltage remains high. And high reliability and robustness for different driving cycle, and low cost and small in size of the motor is the most important thing, because today people want that it should be connected to the wheel. They don't want an extra space in your car, in the within the vehicle. So that is why people are taking this whole motor into the wheel. So that is the So there are a lot of challenges that a typical traction motor drive design, which can satisfy all load conditions and fault tolerant switching converter, where if you see, you need the modular switching converter where you can add the module and bring out the module so that fault tolerant can be achieved. And also the controller and integration and deployment in the vehicle, because it is it should be vibration proof. It should absorb all kind of the vibration still, and both temperature range also, when temperature increases also, it should also operate perfectly. And torque speed requirement is in the typical drive cycle, and fast and ripple-free torque response. These are the main challenges today in the electrical vehicle. So any motor you design, and that motor must give these characteristics. So before going for the electric vehicle, the first motor used in electric vehicle is DC motors. So DC motor was widely used initial days in the golf car. If you go to golf car, now you go to our in the airport, everywhere we use the DC permanent magnet DC motor. And DC motor, because it is a highly decoupled motor and you can easily control that one. Then from the battery, you can directly drive that one. So 750 watt to 1.2 kilowatt DC motor can be used for a passenger drive. So there are different kind of DC motors, some series compounds separately, but mostly in the electric vehicle we use permanent magnet DC motor, because when you don't require an excitation winding extra. So that is why we have a permanent magnet, then as a field, then you have a windings so that you can control the speed of the things. So there are a lot of applications also. I have shown here as one of the application is in the steel mill, that how 4-quadrant operation is operating like this. You can see here the big hot slab of iron comes and the DC motors are there. They very coordinatedly they controls this one. And it was a very popular motor and everywhere used this one. Especially we use it in the servo motors. Then we come to the AC motor, and in 2008, the first Indian Railway AC motor came, which is running from previously we used to have the DC series traction motor in the Indian Railway, but after this 2008, first 1998 is the first AC motor based traction motor drive came, which is running from Lucknow to Delhi, Shatabdi train. We purchased it from Australia. After that, WP7, if you see in the Indian Railway, in the engine, there will be written WP7. The WP7, all those are the AC drives, okay, induction motor drives. And then synchronous motor drive, nowadays it is very popular, especially in the wind power, permanent magnet, synchronous motor and generator, they are very popular today because they have a high power density. And this magnet, the synchronous PMSG and PMSM, they both are used in the electric vehicle as well as a high power wind turbine. Up to 2 megawatt also people have developed this one. And then we have a switch reluctance motors. So when we see an adjustable speed drive, so what is the adjustable speed drive? That means you can control the speed. For example, if you see, just I remember when we purchased the generators for 100 kVA generator in IIT Patna. That time we were not looking at whether it is variable speed or 5-star rated or anything, nothing. So we purchased simply. Even if you have a 5 kilowatt load, you have to run a 100 kVA generator to supply that one. Waste of lot of energies. Whereas nowadays you will find there is a adjustable speed drive. If you have a 5 kilowatt, exactly the generator will be 5 kilowatt. And that is what in your house you have energy efficient coding. You give 5-star rated. And these 5-star rated are very, very important actually when you take this. So this adjustable speed drive gives that one. So before going to variable speed drive, there are converter feed drive, PSI or voltage source inverter feed drive, current source inverter, side source inverter. So first in the first phase in
Kindly
India,
respond your roll call.
there
Roll
was
67. Hello. Yeah. 68. 69.
Sir, KVS sir, Chaudhary sir, your mic is on.
71. 72. 73.
What is that number actually?
75. 76. 77.
May I know what is that numbers?
Yes, sir, you please carry on, sir.
May I know what are that numbers?
okay, can we continue? Hello?
Yes, sir, please continue.
Okay. So in the India government, we first in the phase in 1994 that our traction converters, especially high power traction in Indian Railway, there are 6,000 HP locomotive, and this GTO based power converter was introduced. Then after GTO, the GTO based power converter used for the drive and IGBT based power converter we used for small auxiliary supplies. And then in phase 3 in 2007 onwards, we used both the converter as a IGBT based insulated gate bipolar based converter. That is why there are different kind of multiple GTO based power converters we use, and there are different kind of this electrical multiple unit where different high speed also we use. So typically a power converter of auxiliary converter, if you see, we generally use 70 kVA or 115 kVA, and we purchase all the converters from outside the India, like Alstom, Siemens, General Electric, they give. And this is the main controller of this converter. And if you see inside, if you go inside the train engine, especially if you go to Chittaranjan, electric locomotive, you will find these are the structures, okay? So the main controller and low voltage switch gear, then battery, then PWM converter, then filter, and all the cabling other things. If you see, the drive is the heart of all kind of traction locomotive, and almost all AC drive used in the Indian Railway are imported. We don't manufacture here in India. And even if I became astonished when I visited to the Institute for Solar Energy in Gurgaon, they have a test facility up to 10 kVA grid integrated inverter. So we do not have a high power inverter testing, whereas we develop also more than 400 kVA inverters. So this is our traction drive. If you see the AC traction locomotive drive, you find there is a overhead line and then there are a pantograph. In the pantograph, you can see there is a main transformer, which is called the horizontal transformer. If you have seen in our power system, there is a vertical transformers are there, but this is a horizontal transformer. And from there we convert and there is a rectifier or active rectifier. And then we feed through this converter to this control this our electric motor, okay, wheel. So this is, there are auxiliary for the cooling fan, motor blower, compressors, all those things are integrated together. If we see this typical thing, overhead voltage is from 19 to 27 kV. So that and what your requirement? 4 quadrant operation and 2 traction motor per inverter is connected. And that is how the design was. So when there is a high power converter, you can see the challenging is high power switching converter design, integration is major. Then there are different kind of loop control, okay, for closed loop control. And this is the simple DC drive by which you can control the DC drive simply by using a potentiometer, and you can control the speed. A simple speed control is given here, but it is used for low power drive. Then if you go little advanced control is the cascaded speed control, and you want to control the speed very precisely, and all kind of the closed loop control when you require the high performance application. This type of control we use. So there is a current loop and there is a speed loop, and that way it will control. Then conventional AC drive, we have an inverter feeding to a induction motor. Induction motor can operate in 4 quadrant operation, but you can see that in the front end is the diode bridge rectifier. So when this induction motor is 6000 HP, when they rotate, they have large storage inertia. So when you retard those things, those energy will come back, that kinetic energy will convert to our DC link capacitor will be overcharged. So there is no path for feeding to the grid. That is why the front end rectifier is replaced with another bidirectional converter, which is called the utility friendly converter. And there are different kind of the converter topologies, like 2-level converter and a multi-level converter. So these topologies are used here. And these topology used in this power modulation circuit. So then we have a different kind of AC voltage control, AC motor control. One is scalar frequency control or VIF control. And second one, field oriented control, a direct and indirect. So field oriented control is very interesting because it goes under the high performance control. What is the field oriented control? Field oriented means we orient the field according to, because if you see an induction motor, you have a starter and you have a rotor and you have an air gate. And these three have a different speed. For example, starter is a stationary. Rotor rotate at mechanical speed or speed at NR. And the air gap plugs rotate at synchronously speed. So whatever field you oriented, that became field oriented control. So that we will discuss little bit in detail. And then we have a director control. And today, everywhere we use this director control because it is very simple to very simple to apply to these drives. So first one is our scalar control. We control the magnitude and frequency, not the phase angle control. Like today, if you see in our irrigation system, I remember in our childhood, when we go and see a pump motor, there is a starter, then there is a running. Once first you start, then you run. There was star, delta, starter. But nowadays, every induction motor comes with V/F control, even a blower, even fan motor, everywhere we come with scalar control because it is a very simple control. And scalar control is this one where we have a speed feedback, and then from the speed, actual speed, we measure from this and then pass it through the voltage controller, and then we have a voltage controller, then we generate the switching signal and fed to this inverter control. So that is why this is mainly used in the pumps, fans, centrifugal, then the conveyor belt. So this type of control we use. But first in the 1900, around 1969, there was a professor and he gave the theory of the trans-vector control. That means, you know, a DC motor, the field and the both the field axis and the armature axis, they both are perpendicular to each other. And when you vary this armature circuit current, it doesn't affect on the field. When you vary the field side, it will not affect on the armature. That is why completely decoupled motor. So all kind of servo motor we use the DC motor only. Why? Because completely decoupled motor. So that is also directly you can control the torque, directly you can control the field also. So that same concept that if we want to bring to an induction motor is a highly coupled motor, three-phase motor, and A phase current you vary, it will affect on B and C phase. When you vary B phase current, it will affect other two phases. Like this is a very highly complicated machine. That is why if you read the book by Professor Vidya Sagar, Nonlinear Control. So he gave first definition, the system, the induction motor is a highly nonlinear device. But most of the time we study the steady state analysis, so we do not take care of those things. So this vector control or the trans-vector control was initial name. It is a highly nonlinear and highly interactive and a poor torque transient response. But the induction motor is robustness. Once you put it, it will run for 25 years. You no need to, whether there is a scorching heat, very cold. I remember that when I was in Abu Dhabi Petroleum Institute, and now it is called the Khalifa University, but that time it was Petroleum Institute when I was. So we will go in the desert. We will go for 1 hour, 2 hours, then we will dig. So all the induction motor, there are divers, they will dig inside the earth to find out whether petroleum is there inside or not. So what we will do, sometime we will run that a generator, then induction motor as a driver. So they will dig whole night. So we will just run today. Again, tomorrow we will go to check whether it is properly drilled or not. So there was a driller. So if you find whether there is a lot of there is a oil or not. So it takes 1 or 2 days like that, 3 days also sometime it go. But sometime what happened, when this induction motor is rotating, sometimes the induction motor itself burnt. So next day when we will go, we will see that the induction motor is already burnt. And because of that one is the power quality problem. Power quality problem because directly takes from the generator and usually in the motor, there are no power quality. So large amount of harmonic current generator, which produces a large amount of heat in the generator, though it changes the resistance value, and as the heat increases, resistance value will change. So loss will be more. So that way the efficiency come down, and that way heated and they will burn. Sometimes the insulation failure, sometimes bearing failure, something will happen. So like that, if you see, the induction motor are robust. That's why they would put in the desert. And in the desert, sometime I remember once we were searching the motor, where we dig actually, only without map and without the compass, you cannot find that place. Actually, it is everywhere the same you will look. So where you put your motor, you do not know. Sometimes there is a sand particles, sand will come and they will also sometimes cover. So that was the induction motor are very robust and high torque to weight ratio, less maintenance, and flame proof. You can put in the near the fire also. So that is why this transvector control came into picture so how they want to do, like the torque is depend here that from depend on the armature current and field flux, exactly like this we can make it. So vector control are just to control the torque and flux independently like a DC motor. That is why a reference fluid theory is used. And what is that reference fluid theory? That I will tell you now. So do you see, this is a control of amplitude and angle are called the vector control. So this is a reference frame theory. You see, the starter here, we have, this is my starter, okay? And the starter winding, and this is my starter B phase winding, and the starter C phase winding, A, B, C. And what we did, we took two axes, okay, like, sorry, this is not the, so let me end here. This is my B phase, this is my A phase, and this is my C phase, okay? 3 phase, okay? Now, I took an imaginary axis, which are perpendicular to each other. This axis I have taken, maybe I'll take other color, so that may be little bit very clear, okay? Try to understand, because most of the time, you will find this, when we control a motor, we most of the time make a mistake because we model in the some reference frame, but we design a controller in the other reference frame. So when you have a different reference frame, most of the people, they make here is the mistake. You design the model the motor in the starter reference frame, design a controller in the rotor reference frame. So automatically, there will be a lot of differences in the performances. So this is what A phase, and this is my B phase, and this is my C phase. Now, I took an imaginary frame where this is my two imaginary frame, D frame and Q reference frame. They are both are perpendicular to each other, 90 degrees here. And this exactly all the parameters, whatever there in this A phase or B phase and C phase, all is transferred to this 2-phase. So we are not changing anything in the induction motor. What? In the imaginary axis, we transfer all these parameters to D axis and Q axis, which is perpendicular to each other. So when this D and Q axis, similarly for rotor also we have a D axis and a Q axis. Rotor also having 3 windings, A, B, C phase. And when this axis, this D axis is locked with the starter axis, this is called the starter reference frame, okay, or stationary reference frame, okay. And when this D axis is connected to the rotor axis, this is our rotor axis here. If you locked with the rotor axis or aligned with the rotor axis, then this is called the rotor reference frame. And when you connected or aligned with the air gap or that is called the arbitrary reference frame. These 3 reference frames are very, very important. And sometimes if you see Dr. Bimal K. Bose SC drive, you see they rotate anti-clockwise rotation, okay? The vectors are rotating anti-clockwise. Whereas if you see Peter Vass book, which is English, they rotate in the clockwise direction. That is also one must be very careful. First, you must follow American standard or UK standard, like in America also. So people will drive on the right hand side, whereas in the UK they will drive in the left hand side. So similarly, this also they rotate anti-clockwise and Peter Vass rotate in clockwise direction. So when you rotate anti-clockwise direction, first D axis will come, then Q axis. And when you rotate in clockwise direction, first Q axis will come, then D axis. So there you should not be confused, and one must be very careful when he is modeling this type of converters. Okay. Then when we have aligned with the starter, then it is called the starter reference frame. Aligned with the rotor reference frame. Aligned in the air gap is the arbitrary reference frame. So what is that reference frame? That is nothing but we want to make the relative speed between the 2 vectors the same, or the relative speed is 0. Like you see it in if you go to Howrah railway station, the 2 trains are moving parallelly and they both are moving at same speed. You are sitting one train, your friend is sitting on other train. If you look each other, you will feel that they both are stationary. So exactly similarly, when you put in the rotor reference frame, all the rotor parameter and the parameter here, they will behave like a constant. That is how you can design easily a controller. Anyway, there are many concepts, so we can go on discussing, but I have to go up to advanced level, so a lot of things need to be discussed. Okay, so anyway, the torque is depend on you can see after a lot of derivation, I didn't put any mathematics, just I have the torque is depend on the rotor flux and starter current. You can see that this is a completely decoupled control. And there are 2 kind of vector control. One is called the direct field oriented control or direct vector control or indirect vector control. So when you observe the flux in the air gap, that is called the direct vector control. When you estimate the flux from the current and voltage, that is called the indirect vector control or indirect field oriented control. So these are the just basic block diagram that how to control the indirect, direct and indirect vector control. You can see that this is the indirect vector control because you estimate this one, this from this current and the voltage signal you took and estimated that, and you control this. Then we have here directly you put the sensors and measure the flux. This is called the direct field-oriented control. And these are the some of the result, the speed and the torque during the normal operation. So there are a lot of limitation in the vector control because you need to require very accuracy response is required. The direct torque control is robust and very simple control. So what is that control? There is no transformation matrix are required. So we have a speed controller, then a torque controller, and then a hysteresis controller. Then we select accordingly the switching system. So here, direct torque control and flux control, no coordinate transformation from ABC to DQ or ABC to alpha beta to DQ, park transformation. Those things are not required here. That is why very fast it can work. No current regulation loop, no encoded, and encoder are required for this one. So this is a two-level inverter. And this inverter is a nothing but you have an like a IGBT, and there is a anti-parallel diode. Okay, here is anti-parallel diode which is connected. So each switch is exactly like this, a bidirectional switch, and this is feeding to this induction mode. Now, these are the voltage vectors. So you know, this is the space voltage vector, and this is V1 plus minus means if you go back this. So for example, plus, minus, and minus. That means this switch A is on, then lower two switches are on. So minus means lower switch on, and plus means upper switch on. So this is the voltage vectors. So you can have how many combinations? We can have 8 combinations, V0 to V7. And there are 8 active voltage vectors, these 6 voltage vectors, and 2 null voltage vectors where output voltage is 0. So 2 null voltage vector and 6 active voltage vector. And in this 6 voltage vector and null vector combination, we try to develop the torque and flux as per requirement. So if you see here, the direct torque control is nothing but this. This is your flux. Now I want to increase the torque and flux. So you can choose this voltage vector. So when you turn on this voltage vector, this will increase this, your torque and flux. And you want that it should remain nearly constant. So U3 are chosen. When you want to decrease, you can decrease by using the flux here. That means you control the flux between this range or between this two, between this limit. And this is called the hysteresis current or hysteresis current, hysteresis control. Okay, between that hysteresis band you want to control. So what is the torque? You can see here. The torque can be depend on this, the phi s and phi r, and sine SR. SR is the angle between the rotor flux and stator flux. So changing rotor stator flux and rotor flux, they gives a very sluggish response. So changing in this angle gives you a very quick response. So that is how the simple estimation. This is what is the stator flux, you can just Vs minus IR Rs into dt. That is a simple equation, you can get it. So this way, you can develop a switching table for controlling the both torque and the flux. So this is the switching table, and this is +1 for increasing the torque, and -1 if for decreasing the torque. Similarly, +1 for increasing the flux, and minus or 0, that is for decreasing the flux. And this we will, these are the few mathematical equation. I am not going in detail. That mathematics you can see. Based on that switching table, you can develop a switching table at what sector, because each θ1 is around 6 sectors. So each one gives from 0 to 60 degree. Okay, each is 60 degree duration. Okay, in this 60 degree, which vectors, whether V2, V3, V4, V5, already given before, that these how it will be chosen. So these are the V1, V2, V1, V2, V3, V4, V5, and this is chosen, and this is this optimal switching table is developed, and after that, this is our motor control. The controller is, you have an induction motor, you can measure the speed, and from the voltage and current, you can estimate the flux and speed, and then there is a torque estimation, and through speed controller, you get the torque reference, compare this torque, and pass through that hysteresis current, the hysteresis controller. Then we have a switching logic feeding to this inverter. So these are the results. You can see here, this is the torque. So when this torque, you can see that this is during ramp up period of the speed, the torque is very high, and then again when it reaches to the steady state, the torque is at reference, or the no torque or stalling motion, or at this is a zero load torque. Then again you applied a low torque, you can see that this low torque is increased. And these are the few results. And this is, we use the multi-level converter for designing for the very high power drive. So this is nothing but the overall setup of that multi-level converter. And you can see that this is the multi-level converter. So if you see here, this is the block diagram. So how it is controlled? Is the multi-level, when we use the 3-level for the high power application, we have the 27 voltage vectors. And 27 voltage vectors, you can easily choose the different voltage sector combination so that they are improved. It can improve as compared to 2-level converter what we have used. So based on that, we developed a modified switching table. You can see this is for a 3-level switching, 3-level power converter, and this is that these are the switching table, and these are the 3-level power converter, and this is called the front end converter. This part is your front end converter, and the front end converter, you can see this is the synchronous link reactor or the inductor. Okay, the synchronous link inductor, and then you have a motor side control, and this is another 3-level converter, and this 3-level converter is controlling this induction motor. So one is in the front end, and front end is utility friendly. What do you mean by utility friendly? Utility
Excuse me, sir. Sir, your mic is off.
Is it okay now?
Yes, sir. Now it is audible.
Oh, okay. So when the utility, both voltage and current, they are in phase. That means you can operate at unity power factor. Unity power factor means voltage into current into cos phi. So when cos phi is 1, automatically you achieve the maximum power, or you don't draw any reactive power from the grid. So that is why it is called the utility friendly converter. So now all the drives or all kind of drives or electric motor control, we require this one. So both the converter we control in the converter are controlled independently. Front end converter is the hysteresis current control. So this is what is our complete control. This is a 3-level converter, and 3-level converter, you can see this DC link voltage is measured, and you have a reference DC link voltage, and this is a PI controller, and we have a hysteresis current controller. Then this is our lockout and encoder circuit which run this motor, and we have a 2 DC link voltage here, you can see. Then we have another 3-level converter, which is nothing but it is a direct torque control method we use. Here we have a load end converter. It is operated under direct torque control, and we measure the speed through the speed encoder. Actual speed we have applied here. Then we have a PI controller, and from here we measure the current and voltage. This voltage and the current is measured here, and we estimated the torque and pass through this hysteresis band, then switching table and switching logic, and it is it turn on this one according to your load requirement. So this is the high performance control. And if you see, this is our drive, and these are the result. You see here, the both current and voltage, they both are in phase. You can see here, one of both current and voltage are in phase. In phase means they both always operate at a unity power factor. Power factor is 1. And you can see when you applied a torque, so current increased. As soon as current increased, the DC link voltage dropped. So similarly, this is the simulation result, and exactly this is the hardware result, or the you can see that the hardware result also, it is nearly unity power factor operation, you can see here. And also, like in the simulation, the hardware also, you will see there is a drop in the speed because it is a closed loop, it is again the gain. So there is a change in the torque. So these two, you can see that both the hardware result and the simulation result are exactly matching. And this complete hardware also we implemented, okay, with the two personal computers. There are one PC which controls this direct torque control, another PC which controls this, the complete hysteresis current control. And there are lockout and gate driver circuits we used. So then there are different electromagnetic torque according to R1 diode cycle. You can see here there is a quick reversal in the torque, and still this is also showing, you can see that very quickly torque response transfer. So this is how the high performance controller can be used. So this is a urban diode cycle. When you are driving in an urban road, this type of torque profile we get, and this is our speed. You can see that this is the miles per hour. Okay, so this speed is the miles per hour, and this is our speed reference, 30 miles up to 50 miles, and this is the response. So then we have simulation result for the rural drive cycle. So this is the rural drive. When we use in the rural area, how this will drive actually, you can see. So this is the rural drive cycle. You can see exactly torque is following to the reference torque. Now that is how this is very beautifully simulated, both the system. And the complete hardware, you can see here, this is the complete hardware circuit. And we supply from this auto transformer, and this connection came from here and to this, and to the here, this place, from here to all this, three inductors are here. And this, there is a one converter here. This converter is acting as a AC to DC converter and feeding to this converter here. And this is the DC to AC converter, which is feeding to this induction motor load here. And this converter is controlled by, this converter is controlled by this PC, and this converter is controlled from this PC. This is controlled by for this, and this controls this converter. So the complete drive unit is developed, and this is made for the Indian Railway only. And before that, we tested the high performance. And you can see here, when there is a reversal of speed, you can see that this is a simulation result and this is a hardware result. Exactly they are matching with each other, that the reversal, speed reversal, everything you can model that. So typical, you can see that these are the trajectory. This is the flux trajectory, both this and DQ axis flux, and this is our system. And if you want to see, this is our hardware setup, and you can just look into this, that how to develop this torque test you can do by using, we have a dynamometer load, and this dynamometer load you can load it, and different kind of torque profile you can generate by this dynamometer load. Okay, so this is possible here. So this is fed from this two-level inverter, and you can see here this voltage, and according to torque, you can apply different kind of torque, and you can test your drive setup. Is it possible? Okay. So anyway, there are complete hardware was designed, and then we have close agreement with the simulation, and then we will go little bit about the four-wheel drive. Okay, four-wheel drive which is recently coming into picture, and so the very beautifully, when that is why there was one Ministry of DT, the Department of Electronics and Technology. They asked me once that, sir, can you develop a electric vehicle for hill region, which is very, because the in the generally the IC engine, they generate large amount of pollution during the when they are riding on the top of the hill. They produce a lot of noise, and efficiency come down less than 23%. So they want some kind of electric and both one electric vehicle, one electric engine, and another one is the IC engine. They both want a hybrid kind of thing. So they requested me, sir, can you develop one motor drive for this type of loads? So we started developing this one, and how you will analyze. So dual motor concept come into picture, and that project that we have recently also published. So if you see this car moves, there are different kind of force. Okay, there are resistance, tractive force, vehicle acceleration, braking, stopping distance, so many things are there. And that we can write down a simple in a torque equation. And this I am not going in detail into vehicle dynamics, because if I will go to vehicle dynamic, so we will be completely discussing the mechanical system. So I will not go in detail into mechanical dynamic of the system, but we require this torque, okay? So we did a lot of derivation, and you will see that in dual mode we started. So there are different classification of electric vehicle, this type of electric vehicle, but we will go to, because we have already, it is nearly 4:52, so we should discuss more practical things. So these are the different hybrid structure, series hybrid, okay? F means your fuel tank, okay? And E means your IC engine, and G is your generator, your battery, and P is your power converter, M is your motor, and T is your transmission, okay, system. So you can see that series parallel hybrid, parallel hybrid, complex. These are different things are available, and in my book I have given very detailed of these hybrid motors also. So the control of electric motor is that you have a charger, you have a battery, and you have a DC-DC converter, then inverter, then motor, and to the wheel drive. So today we will discuss dual motor, differential 4-wheel drive for electric vehicle. Okay. So this is recently, this in 2021 only, this is published, this paper. So what is the dual motor drive? Dual motor means two motor, one motor in the front 2 wheel, another 2 motor and the rear wheel. Okay, back side, back wheel. There are 4 wheels. So 4 wheel, 4 motors are there. 2 motors are there. That is called the dual motor. And we take in this one as an induction motor, and we use open winding induction motor so that you can feed from both sides, so the efficiency can be improved and the battery requirement can be reduced and the line current can be also reduced. And then we have a modeling, then differential 4-wheel drive we will discuss, then the battery, which is very important, and how the battery discharges, that is also very important. And I will speak something further research in which area, and if you want to do on dual motor drive, which area research you can develop. That is also another important factor. Okay. So if you see that nearly 1/3 of the ground vehicles is expected to use by electric traction by 2030. So people are putting now a lot of energy into the electric vehicle development only. So that is why there is that we also must run according to the requirement of the time. So that is why mass movement like electric car, buses, now buses are available also. And in the Bihar government, a lot of electric bus are moving between Patna to IIT Patna. So that is what it is very. So PMSM also very good for the better than induction motor, but the problem is that the rare earth magnets are very costly and we have to depend on China. So that's why they're very, it has very limited availability. So people prefer the less magnetic motors, okay? Motor without magnet, such as induction motor and switched reluctance motor. So compared to SRM, induction motor is more efficient and have the SRM is more efficient and cheaper, but have major disadvantage are the vibration, noise, and torque. So one of my students, he's in IIT Rotor. So he was telling me, sir, I was working on the SRM motor, And in SRM motor, there was not a single paper available on the fault diagnosis of SRM motor, and he developed that one. So he was telling, but still the noise and torque ripple is the biggest hurdle in using for the electric vehicle. And the induction motor is a better alternative at a higher power rating. If you go above very high power rating in 50 HP and above, so the induction motor are very. So that is how the Tesla motors use induction motor as a propulsion system. So the induction motor size increases with the power demand. So that is how the induction motor, you know that requiring a high inverter DC bus voltage, high voltage problem addressed by using open end winding induction. So open end winding, when you open the winding and feed from both sides, that becomes the voltage can come down, current can come. So conventional this power is started by two voltage source, both end of the starter winding. So what is the advantage of dual two-level VSI driving open end winding induction motor? The advantage is you require half of the DC bus voltage. So voltage level decrease means the stress on the switch reduces. Second one, that it can power from the two converter. So the number of semiconductor switches, they remain same, but the requirement, the power requirement will be come down. And modular circuit, so simple control structure. Both are modular, so a very simple control structure you can develop, and you have better the THD and lower torque ripple. Okay, so switching frequency also low, so that your efficiency can be more, because switching loss will be less. And that is why because the high reliability, because they have fault tolerant capability and absence of neutral point variation. I will tell you, one of my students, he just completed his PhD, and we have a 5-phase induction motor drive. In this 5-phase induction motor drive, and he could able to run that motor up to 3 phase. So that type of facilities are there in case of the induction motor. So this is a induction open end induction motor, right? The open end winding, and you have two voltage source inverter. You can see the two voltage source here. This is one voltage source inverter feeding to this motor, and here is another voltage source inverter, and this is the switching system, and the dual two-level VSI are fed from that this induction motor. And when we feed this one, and if you see, these are the voltage vectors. Okay, the switching state and switching group of this voltage vectors, and these voltage vectors are individual two-level voltage vectors. You can see that there are a lot of combination will come, and although when you take a two-level, three-phase, I have shown you 8 voltage vectors. Okay, maximum you get 8 voltage vectors, but here you have 8 from this side and 8 from other side. So both are dual. So you get nearly 16, and then you can combine also, you will get. So anyway, so if you see this state space modeling, this is our state space modeling, and I'm not going in detail to mathematical modeling. You can go to this paper, which I have already told you. This paper is published recently. You can see if you are interested in dual motor drive induction motor. So then this is the model of the, you can see that this is the mechanical model, which is like a conventional induction motor. And this is the electrical model, which is there. And this is the state space model of the complete the system matrix, and these are the starter magnetizing coefficient. They are defined this one. So if you know the modeling of induction motor, these are the same thing. There is nothing different. So different powertrain arrangements such as this front wheel drive, rear wheel drive, four wheel drive, all wheel drive. There are four kind of this the powertrains arrangement are there. So front wheel drive, when you put the motor in the front wheel, when you put the motor in the rear wheel, that is called the rear wheel drive. Four wheel drive means four motors and the four wheel is or two motors and the four wheel. That is also we call the four wheel drive. And four wheel, generally four motors are connected, but dual motor four wheel drive is two motor, but it drives four wheel. And all wheel drive are also employed. So four wheel and all wheel drive can be either in wheel or on board also. So then the cost effectiveness and reliability is poor in those drives. That is why there is no fail-safe operation is there. So that is why in wheel drive are more compact drive but complex control structure. That's why differential four-wheel drive gives better control and stable operation during turning as well as forward acceleration. So four-wheel drive with induction motor as a prime mover is used in this discussion. So this is the four-wheel drive, the dual four-wheel drive with a dual motor, okay, a dual winding. You can see that this is one winding, okay. So you see here, this is a battery pack which feed from here to here and from here to here, and this is another. So these two VSI controls, 1, 2 controls the front end, 3, 4 controls the rear wheel. So these two and vehicle control is this one. So these these two motors control the complete electric vehicle. And there are the mass of the vehicle and the front, the distance from the four wheel, and I'm just showing you the diagram here, okay. So this is our four wheel, okay. So this four wheel are run drive by two motors, and this M is the mass of the vehicle, H is the center, the height from the center, and then this complete system is modeled, okay. So the F, ZL, these are the longitudinal acceleration, okay. So then there is a lateral acceleration, okay. And this complete unit is developed, okay, this four wheel. And then this is the mechanical, your rear wheel, the force, and the front wheel force, okay. So these equations are there in the paper, and all derivation also we did for this one. And when vehicle is standing, then at constant speed the forward force or the forward wheel, front wheel force are component of the normal force. And then there are different kind of force applied when the vehicle moves, and that is called the vehicle dynamic. And this vehicle dynamic you can understand from the different force acting on this vehicle. You can see here vehicle force, and when it moves in the front direction, Vx is your speed, and then the friction which is extracted by the wheels, and also during the turning that wheel they divide the different kind of force. So all these are developed here, and the tires spinning axis and slip ratio occur when the F at the tire when this movement applied, then that time all these force are applied, and then we can develop the completed for the acceleration, and this is depend on the tires pointing direction to the tire of the vehicle motion. And this motion, all the thing, vehicle dynamic, I am not going in detail, but you can read that paper, very nicely given. Because so this is at the time of acceleration, when the side slip ratio is this one, so then it is called, it will operate as a deceleration, okay, retarding force. That means that time the vehicle can give power, the deceleration, the kinetic energy can be released to the, and when acceleration, it will drive the vehicle in the front. And similarly, during the longitudinal friction time, so slip ratio also, similarly we get for both the front wheel drive and the rear wheel drive, the complete control can be designed. So when during the turning the speed, when you turn the speed, you can see the front wheel to drive to the two wheels, they turns in this direction. You can see they are turning. Okay, the front wheels are turning. When you turning this one in a turn, in a some curved surface, when it is moving like this, then this is your the R, which is nothing but your center. This is the R is L divided by 10 delta, and V by R is the turning speed. Okay, so this way the control effort are more than this. You can see this one very vividly in our battery when it discharges. So that is why this gives the feedback speed control to the complete control system, and then it will regulate the speed error and corresponding the driving torque in the for the rear wheel as well as the from the front wheel. Okay, front motor and rear motor. So that is how this torque, this torque in this the requirement is nothing but it depends on the both the forward motor as well as the rear wheel. So this is the speed control unit. This is a simple GPS unit where you can find out the location, what is the geographical area, everything, and you can find out. Then accelerator, steering angle control you have, and brake pedal. Okay, when you brake, give braking. Okay, so like you drive a scooter, so when some car is coming, automatically your mind will process and it will tell your hand that you please slow down. So exactly this is also the similar kind of thing, which is you can see here that this is the front and rear wheel braking system, and then front and rear motor speed control, and then we have a speed controller, PI controller, which is given. This gives the torque reference. Okay, one torque reference for the front wheel and another torque reference for the rear wheel. Okay, and then we compare, and this is the front and rear wheel motor control. So if you see here, we use here the two VSI are feeding to this open end winding motor, and here also two VSI feeding to this open end winding, and this is the two battery pack. Okay, these battery packs are used for driving this one, and there are a lot of technology that how to control this battery discharging limit also. So then we use the direct torque control, like I have already discussed the direct torque control, that we have nothing but we have a speed encoder. We get the speed from here, and this speed is fed. The speed is fed from here to speed control unit, and speed control unit gives the reference torque. Okay, here, and actually that torque is compared and the hysteresis and feeding to switching table, the switching table drives this one. And there are ABC2 alpha beta and alpha beta. Then you have a torque and flux estimation block. And this is that how you choose the voltage vectors. So this there is alpha and beta axis, and you can see that front dive and these are the two sectors. Okay, the sector 1 and sector 2, where you select the different voltage vectors. Okay, so this is our flux and this is our torque, which is we have already seen in our direct torque control. So I am not going in detail. Then look up table method for the fault tolerant operation. Okay, when there is a fault in one phase, for example, here there is a fault you can introduce here. So when one phase is at fault, for example, so during fault operation, how this motor will run? So exactly because this is disconnected, but this is a fault tolerant. During fault tolerant also, this open end winding you can run this as a lower torque. So that is of the advantage in this this type of technology is advantageous because this technology you can see that during fault also you can develop. So during fault period, the K is this here. You can see that the K is the sector. Okay, K is 0 to 6. So in this TS and subsector AK means sector 1, BK. You can see here, A means upper sector 1 and B means lower sector 1. Okay, so similarly, if you go here, there is a AK and BK, and AK and BK. Accordingly, you choose the switching table, and this table you can develop. And then battery lookup table for battery state of charge or power balancing, because there is a little unbalance in the battery. You know, in the Tesla car, they use each battery cell is a 2-volt battery. Why 2 volt they use each cell? Because even if in a string, if 2-volt battery is discharged, so if 2-volt battery is discharged, the 2-volt battery, when it is discharged, that will not have any effect on the complete battery structure. So that is why they take generally electric vehicle, they take very, very low voltage level batteries and they put in series and parallel combination. So this is what the beauty of this lower voltage level. So lookup table for this battery is this one that you can see here, that this lookup table for the battery and charge balancing, and you can look at this one. Both all the complete control system is put together, and this is the complete control or the power of the battery balancing. So what we have added here, you can see here, we have added one branch here for balancing the battery, which is very important in a electric vehicle. If everything goes fine and one battery discharges completely, your drive will create a different kind of noise, vibration, and you cannot move further. So that is why the battery control is battery management is one of the biggest challenge in this type of electric vehicles. So that's why we added here, you can see here, you measure this IDC1 and IDC2. This is your IDC1 and IDC2. Okay, you measure, and this measurement you put an SOC calculation based on that switching table, and you put this one in the switching table, and this is fed. So this is how you control the complete unit, and this is our experimental setup. Okay, this is a battery emulator, and this is a VSI. You can see there are four VSIs. Okay, there are four VSI, 1, 2, 3, and 4. And this switch you can use for fault tolerant. You can create fault here, and these are the sensors. Okay, then these four are this control flow through micro LED box in the D space, and you have a dual motor drive, two motor. Okay, so dynamometer set and motor, and some electronics load are connected, and this is our experimental setup. Okay. So now we come to the experimental result. You see here, this is the FM is front motor and rear motor. Okay. So now you see when there is a so the motor fault during acceleration. Now during acceleration stage, motor run, and during that stage, suddenly there is some, you see, this is the acceleration stage, and this is the acceleration stage. So during that period, there is a fault. So there is a fault, you can see here. Okay. At this point, there is a fault. So current in one phase. So suddenly current increased and another phase current decreased. Okay, you can see here. Now you can see that one battery is discharged to 0. Okay, another battery is very high. So what happened during this period? Suddenly at this point fault occur. Okay, these are the point. At this point, fault cleared. Okay, because of our switching table, we cleared the fault, and you can see that both the battery, they became again the balancing. So this operate during the acceleration time. If there is a fault, that can be rectified by using our lookup table. And second thing, you see, during acceleration, the rear motor fault. Rear motor means the backside motor. When there is a fault, you can see that the same effect are there, but within a few times, this is completely balanced with this one. So this is possible because of our the lookup table, which is applied here. But you can see that although initially, why we start from here to here, there is no charging, because till this point, the battery were balancing each other, the battery voltage. When balancing battery voltage come, that time we apply the voltage torque. Okay, that is why if there is no balancing in the battery, one will charge very high, another will discharge to very low. So that is why battery balancing is a primary requirement when you start the vehicle, electric vehicle. So that is how you can see acceleration start when the battery balancing occur at this point. Okay, and the current also you can see here, this is the current. Okay. So this is fault during turning. When motor is turning, you can see during the turning, the voltage is, there are unbalance in this voltage, because the motor is turning in a round path, or when turning, you can see here and there is a fault at this point occur. At this point, there is a fault. So as soon as a fault, there is a state of charge, or the battery current are different. And because we have fault tolerant control, you can see that it brings back to balancing condition. So this is possible with this type of dual motor drive. So this for the rear motor drive fault turning is possible. And rear motor during the turning also the same way. We also studied here that this is very, here you can see that there is because there is a turning, so there is a voltage difference between two, because the current drawn, because they will experience a different kind of torque, so that will require different current. So here the fault occur and very quickly it also cleared. So this is the urban drive. Like I have shown you some of the result that this is the urban life, and this is how the speed drive goes like this. Okay, and exactly your torque. Okay, you can see here, whenever it is acceleration, you are getting a positive torque. When it is a deceleration, you are getting a retarding torque. So this is what you can observe in this torque axis here. And this is the battery. You can see here, these batteries they try to balance each other. And this is the motor power, how they draw the power. So then the highway drive, okay, the highway drive, you can see that this is the front wheel power, and this is the rear motor power, and you can see here the front wheel and rear wheel. This is the highway drive. Okay, so actually you go very high speed during that period. So highway drive and battery current, you can see that really balanced and this. And the torque also, similarly, it is achieved. Okay. Now the SOC balancing. So how you will balance state of charge? This is a very important factor. Okay. So SOC balancing for urban drive, during that period, you can see that there was a different SOC here. The battery currents are different. So at this point, the battery they started using the controller by which both the battery under all kind of driving cycle, you can see this is the driving speed in this in this one, the driving speed, the battery always remain balanced. So this is how is the different driving cycle we tested. And with expanded to control facility, we use the high performance analysis. You can see that this is nothing but the battery current. They try to and they become equal, and this is the vehicle speed for the constant speed operation for testing. And the performance SOC balancing during high speed highway drive cycle. Okay, so that is how this is the same hardware result. So anyway, there are many things you need to develop that this can be used for ship engine, aircraft, all the things. And the second thing that the distribution of battery pack and battery management under fault is very, very important. And the extended work can be done for the electric vehicle with a multi-level converter, with a distributed battery, enhanced management. There are a lot of research challenges in the dual motor drive, and anybody want more we have these facilities also. And there are a lot of EV sleep control also, another topic that people, you can look into that. And these are the references. And thank you. And this is our lab for 5-phase induction motor drive. You can see this is the 5-phase motor drive where we feed from this, and this is running this 5-phase motor drive. So this is a high performance controller, 5-phase induction motor drive for ship and electric vehicle. You can see that our students, they developed this 5-phase inverters, 2-level inverter, and you can see this is the current. And you can introduce all kind of also fault here, and completely designed by our students. So there are also a lot of vehicle controllers are available, and I am not going in detail of that one. And there are a lot of prototype design. Thank you so much. So I stop here. No problem. Thank you. So any questions or comments from anyone?
Participants, if you have any questions, please ask your question. Or any queries, any doubt, if you have, you may ask, please.
So if you don't have question, you can, I have given my email address. So if you want anytime.
Okay, when you face any question later on while watching the video, once we will share it, so you may ask your question through the email given by the professor. Okay. Okay, sir. So if there is no question, we can conclude with thank you so much, sir, for your kind cooperation and giving such a nice talk, very informative. And I hope that the participants will really utilize such ideas to their research work. Sir, from my side, just one small token of appreciation. Please accept it, sir.
Thank you very much.
Thank you, sir. If there is any questions from audience side.
I am very much delighted to, sir. Namaskar, Renu Sharma. Especially I am attending these sessions because I want to learn more from you, sir. I know a little bit, but still I want to learn, and that is why so wonderfully all the sessions are going. I'm not able to find out that everything is self-explanatory, sir. It's well explained, and I have taken various snapshots of the various sessions in which you have explained wonderfully from starting from motors, and then you have come to the applications, sir. All the sessions, all the slides are well explained. Application, industrial applications, everything, sir. It's very nice. Thank you, sir.
Thank you. Thank you. Namaste.
Namaste.
Thank you, ma'am. Thank you, sir.
Thank you very much.
Any comment from audience side? Any questions? Okay, so I think, sir, there is no questions. Okay, I have one announcement for tomorrow. Actually, tomorrow session 4, that is I had to take, but one of the professors from Denmark, he has requested to exchange my talk with the session number 10 from Dr. Sanjeev Kumar Padmanabhan, sir. He will be taking their lecture, his lecture tomorrow morning, 10 to 12, and I will be conducting on 28th. So thank you so much for attending the session. Okay, thank you so much, sir. I will be in touch with you. Thank you, sir. Please.
Thank you, ma'am, so much, sir.
So today's session, we are closing now. So you are free to leave the session. All the videos, recorded videos, will be available just after some time. Okay, so let's wait for that. I will be sharing all the videos, recorded lectures or videos to your mail, as well as it will be available to YouTube channel as well. So once we will upload these things to YouTube, you can watch from there as well, or I will share to your mail also. But please wait some time. We need to process it, we need to download it, and again we need to share it. So please be patient for that. Thank you so much. I have shared all the feedback links to your mail. You may give the feedback. You may submit your feedback. We will check the later on for the attendance purpose as well. So thank you so much. You may leave noise. Thank you.